Okay, I think it's time to get started. So first of all, welcome everybody to the 8th edition of the Computer Vision for Sports workshop. We have to see so many both physically here, but also on Zoom. So I just want to give a short introduction to what will happen today. And I just needed that to work. Yeah, so today we'll have 4 invited keynotes. We are very happy to see quite diverse topics. These keynotes will be 40 minutes presentation and then about 5 minutes of questions. So if you have questions here in the physical room, please go up to the microphone. And if you're on Zoom, then please write into the chat, and then we will curate or we will ask the questions here in the room. We also have 4 oral presentations of the submitted papers. These will be 20 minutes, 15 presentation, and then 5 minutes questions. And again, please come up to the microphone. We also have 11 spotlights for remaining papers. For remaining posters, it will be 2 minutes, and you won't have time for questions, but then we'll have a poster session afterwards. We also have Anthony and Silvio present the SoccerNet camera calibration results in the afternoon. And in the end, we also award Best Paper Award, kindly sponsored by EVS Broadcast Equipment. So we hope you will stay out throughout the day and hear a lot about interesting applications for computer vision for sports, all kinds of sports. So just quickly before I let the first keynote on, there's a bit of practical information. This will be streamed to Zoom and the workshop will be recorded. So if you ask questions, this also implies consent to it being recorded. I hope that everybody's okay with that. Lunch will be down in hall D&E, as it was yesterday, and the poster session will be outside of these hall D&E at these locations. So if you have a poster, then please set them up in either the coffee break or in the lunch break that we have beforehand, just to smooth everything. And if you have want more detailed information, then please go and visit the website where all the posters and paper names are listed. And I also just want to recognize the organizers of this workshop. Sadly, none of them could be here today, but they put in a lot of work in curate or in processing the papers and just organizing it. So I think that should be acknowledged. And then I just want to present myself and Andreas, who will be your host today, since none of the organizers could be here. But with that said, I won't take more of your time, and instead I will let Florian Magera and Olivier Barnick from EVS Broadcast Equipment present their paper on computer vision. Sorry?
I just have a question about the poster.
Yeah,
that
of course.
Presented here.
Yeah.
I'm not quite sure that it corresponds to where the stands are located. Currently, they are not located in the hall B and E.
Okay.
So this is for the main conference posters. That would be
No, we're located outside of hall E and D.
So, and for the numbers, they don't correspond to the numbers that we saw in the on the poster themselves.
So where are we located instead?
So there is no structure, it seems, in this.
Oh. Yeah.
Oh, they're not. Okay, I think it's fine. Okay, thanks.
All right. So again, that's why I would like that you put up in the break so that we won't spend valuable time in the poster session for this. Yes. But yeah, I won't take more of your time. Instead, I will let Florian and Olivier talk about computer vision for live sport production. Yes. Just cool. There's some water here if you need.
Thank you. Hi, everybody. I'm Florian Magera. I'm an innovation engineer at EVS Broadcast Equipment, and I'm also a PhD student at the University of Liège in Belgium. So today we are going to talk about the use of computer vision in the context of live sport production. And so to give you an overview of our talk, first we'll present EVS, what kind of company it is, and then we'll dive into our applications in live production. So first, I'll let Olivier introduce our company, EVS Broadcast Equipment, to you.
Hi, everybody. My name is Olivier Barniche. I'm Head of Innovation and Architecture at EVS Broadcast Equipment. And I will introduce you to our company in order for you to better understand the context of the use cases that we will be talking about today. Do not worry, we will keep this introduction to the company quite short. During the rehearsals, it was around 4 minutes. So EVS Broadcast Equipment is a company that is from Belgium in Europe, and that is actually located in Liège, which is, as you might know, the place where we make the best waffles in the world. EVS is a company that is active in the media and entertainment industry, and more precisely in the production domain. So production is what we call production in the broadcasting industry is the process that takes all the camera streams as input and that output the television program that you will see at home on your device. So in the context of a live sport event, production usually occurs in the big trucks that you might have seen around the stadiums. And in these trucks, in order to produce the program that you will watch on television, there is a lot of equipment, and most of these equipment, you can buy them from our company. And actually, if you think about replay servers, which is one of the most common kind of equipment that you find in production setups, we are the leading provider of replay servers in the world. So if you have seen a replay on television watching sport, you have probably seen content that has been produced by our equipment. So our customers are production facilities and service providers, broadcast and media network, and sport event and organization. And they are spread all over the world, and you might actually recognize some of them. And we are also very active in the organization of the technological setup that makes the broadcasting of big events possible. So we've been for more than 20 years involved in all the Olympic Games, soccer World Cups, and basically any big sport event that you can think of. EVS is a company of around 600 full-time members. Half of them work in the R&D department, and our workforce is spread in more than 20 offices, but most of the development occurs in Liège in Belgium, and there are other development offices in the Netherlands, in Germany, in France, and in the UK. We have commercial offices basically all over the world. So there are around 300 engineers that work in the R&D department at EVS. But among them, there is an innovation department, and Florian and myself are actually part of this department. So we will talk about shipping products today, but we will also talk about investigations that are going on in the team, because it is our purpose to do this kind of investigation before taking the decision to turn something into a product. And around 2015, we decided that there was a technological opportunity to investigate around the rise of a deep neural network for video understanding. And since then, we have been exploring how we can leverage computer vision to maximize the quality of content that you see on television when you are watching sport. I will now give the floor to Florian.
So why do we want to use computer vision into live sport production? So there are 3 types of applications. So first, for high tier productions, so productions with a lot of budget, we can help produce more beautiful images or videos, and we can also help storytelling by using computer vision. And on the other hand, for low-tier productions, so production with small budget, we can use computer vision in order to automate the mundane task, in order to create, enhance the quality of the production if it's possible. So for instance, we can use more cameras by using automatically steered cameras. And also computer vision is a way to get metrics about a game, so without adding sensors. So it can be used for tactical analysis or for statistics. So now I will show you a few use cases. So first, I'm going to present the virtual offside line. Then I'll also present the video retargeting. Then Olivier will talk about the automatic steering of robotic cameras. And then we'll talk about various kinds of applications for replays, which is basically why EVS is known for its replay servers. So starting with the virtual offside line. So in fact, this is our first product leveraging deep learning. So the purpose of the virtual offside line is to help referees decide about offside situations. So in soccer, the offside rule is very complex and it's often very difficult to decide. So according to a subjective viewpoint of the referee or a spectator, the offside position of a player might be unclear. So computer vision can help to remove this ambiguity by simply drawing a parallel line to the goal line in augmented reality on the pitch. So in order to do this, we need to have a 3D model of the pitch, and we also need a calibrated camera. So by calibrated camera, we mean a camera, we mean that we know the geometrical transformation that is applied by the camera to the 3D world in order to produce an image. So we need to estimate the camera extrinsic parameters and internal parameters, such as its position, orientation, calibration matrix, and some distortion coefficients. And more importantly, we need correspondences between a 3D known object and its image in order to determine these parameters. So we need a calibration target, which is an object of known shape and size. So the advantage of the sport context is that usually we have a very big object that has very well-specified dimensions, which is a sport pitch. And so we use the sport pitch as a calibration target. And so the next step for us is to detect the sport pitch elements in the image. In order to do this, we designed a new semantic segmentation neural network, which produce 3 kinds of segmentation maps. So it uniquely identifies line intersections and lines in order to have correspondences. And it also segments lines as a binary classification task in order to be used for evaluation. So once that we have enough correspondences, we can estimate the camera parameters by solving the equations of the linear model. And then we can draw an offside line in augmented reality. So here, this situation is quite easy. In fact, we have a defender and an attacker, and we see that the defender is closer to the goal line, so there is no offside. So this was our first application. Now, a new project that we are working on is that with the rise of social media, we need sometimes production that is specifically done for mobile devices. So we call that vertical production, so with an aspect ratio of 9:16. And there have been several examples of such vertical productions, which until now always used more cameras. So there were cameras for the classical production and cameras for the vertical production. So our idea is to automate the vertical production by leveraging the cameras that are already there for the vertical production. So usually there are 2 steps in order to achieve reframing. So first, we need to detect the object of interest in the image by using object detectors or more abstract concepts like silence detectors. We need this detector to work on any kind of content on any type of camera angles. We need it to be consistent across time, and of course, it should focus on the action. Then, once that we know which parts of the image are interesting, we need to estimate the trajectory that will be pleasing to the eye, that will be smooth, in order to produce the vertical projection. So ideally, the best algorithm for us is able to consider multiple trajectories, to propose several kinds of cropping in order to rate the best one to the operator. So here you can see the results of an off-the-shelf algorithm that was used to honor data. So as you can see, there is quite a problem with this approach, because as all the players are moving quite quickly, all of them are considered salient. So the algorithm doesn't work and it often misses the action. So on the right side, you see the same deep neural network that was retrained on all data sets. And you can see that now the only players that are considered salient are the ones that are close or into the action. And we notice also that we lose less often the ball, even if we don't want to frame always the ball, because sometimes we do not want to film it, because in the case of injuries or falls, that's not interesting. So we also noticed that our retrained model was not performant on other sports balls. So we need to build either sport-specific datasets or multi-sport datasets that are bigger. But luckily, eye tracking devices make the annotation of this type of content very easy. So now I'll let Olivier talk about our journey with robotic camera steering.
Thank you. That's definitely a journey, and it's actually the lengthiest part of the presentation. So it's a project that has started with a very simple ND. So we had been working on silency detection, and during one of the many discussions that we've had around this topic, we figured, well, could we use this technology combined with a full pitch view of a game to know where the action is happening on the field, and to point robotic camera to the action at any time in automated fashion. So it looked actually pretty simple, but it took us almost 2 years to reach a stage where such a system could be used live on a real production. But I guess that we made it. It is now a shipping product, and I will try to give you a sense of all the things that are involved in this project to make it a reality. So the idea was to not to completely replace the camera operators with automatic camera, but to add robotic cameras to the setup shooting the game on top of the human camera operators. The purpose is to give to the director more point of view to consider to be put on air without requiring to add human camera operators. So the initial idea was to take this kind of full pitch view and to leverage a silency detection algorithm to locate the action, and provided that we were able to calibrate this full pitch camera as well as to perform real-time camera calibration on the robotic camera streams. It looked actually pretty easy to point the robotic camera to the action at any time automatically. And actually, it worked. This is the kind of silency detection that we were able to get with our algorithms, and the camera was actually following the action pretty well. However, we had robustness issues because we need to produce content that can be put on air at any time, all the time. So the system cannot fail, basically. And in the case of unexpected object being thrown on the field, and which is unfortunately something that happens in the context of soccer game, or during some specific phases of the game, for example, when the game was stopped, the silent C detection algorithm was failing. So we came to the conclusion that we needed to add other source of information to combine with the silent C detection in order to get enough robustness. And the obvious thing to try was to leverage off-the-shelf sport ball and player detector to try to help the system to locate the action at any time. Off-the-shelf pre-trained algorithm were giving already accurate result, but as it is the case in many other situations in this presentation, we also noticed that retraining these algorithms on our own data was actually necessary to get satisfactory result in every situation. And we combine these two detectors to locate the action. And as you can see on this example of results, for example, a tricky situation was a situation where the ball is in the air. And of course, you do not want to point your camera at the ball when there is a corner kick. You want to follow the players on the ground. And by combining the two detectors, we were able to understand that what we needed to do in this case was to focus on the silent C detection and on the player to point the camera, not on the ball detection. So the robustness came from the fact that we were actually combining detectors instead of relying on a single source of information. But still, robustness was improved, but we wanted to get even more robustness. So we figured that there was actually in every game a source of information that we were not leveraging. And this source of information is actually the video feed that are produced by the human camera operators. Because of course, the camera operators receives instructions from the director, and at any time, the camera operators offers a selection on the content on the game, on the content that he finds the most interesting. And if we are able to analyze in real time the content being filmed by the human camera operators, for example, to retrieve the part of the pitch that is being put on in the frame, if we are able to detect the ball and the players in the stream produced by the camera operator, and maybe compute higher level statistics such as the game flow direction, or even recognize some events, because during the course of the project, we came to the conclusion that if you think of events such as corner kicks, such as penalties, such as kickoff, you need special care for these events to produce images that you actually want to watch on television. If we combine all this information that we retrieve from the human camera streams, the human operated camera streams, and the metrics that we got from the full pitch view, we should be able to get something that is robust enough to be actually used in the context of live production. And the last decision that we needed to make was to choose the camera stream that we would analyze in order to retrieve information. And this decision was actually easy because if you think about it, the main camera in the context of a soccer game is on air 80% of the time. So it will be probably the last camera stream to be operated, and we could make the hypothesis that this camera stream would be available on any game. Now that we have all our metrics, we need to combine way in order to get steering instruction, meaning PTZ parameters, for our robotic cameras. And to do that, we actually tried two approaches. The first approach was to come up with an handcrafted algorithm. And this handcrafted algorithm was taking advantage of the dozens of discussions that we've had with camera operators and directors to understand the roles that each camera have, that each camera position have on a sport production. And actually, you need a framing algorithm that is different for any camera position. The second approach was, of course, to try to formulate the framing algorithm as a machine learning problem that would take all the metric as input and that would regress the PTZ parameters from these inputs. So as I've told you, it is very important to understand the fact that each camera has a specific role, and actually in real in real life, the director is giving real-time instruction to the camera operators. So you need to put much care into producing content that matches the director expectations at any time. Regarding the data-driven formulation of the camera framing problem, it actually gave good results, and in many situations, it gives best results than the handcrafted algorithm. Unfortunately, at the moment, it lacks in terms of robustness, which is why we are still resorting to the handcrafted algorithm at the moment, but we have good hopes to replace it with a data-driven version at some point in the future, because if you think about covering other kind of sport, being able to use machine learning to learn framing instruction for a new sport is a very attractive option. So after all this, we were actually able to get a system robust enough and precise enough to be used in a live production. So the system has been tested in some of the greatest stadiums. So we've been to Japan, we've been to Stade Vélodrome in France, we've been to Maracanã in Brazil. It was honestly very exciting to be able to test the system in all these nice places. And we are very happy that after this long journey, we actually made it. I will now give back the floor to Florian that will explain you multiple ways we've been exploring in order to improve the quality of replays that you watch on television.
So back to our core business. In order to do a nice slow motion replay, you need a high-speed camera that is also called a super slow-mo camera. But super slow-mo cameras are really expensive. They use a lot of memory, a lot of bandwidth, and they also are quite big and fragile. So you cannot put as many slow motion cameras as you want around the pitch. So we thought maybe we can use computer vision in order to turn any camera into a super slow-mo one. So this is I will present our last product, Extra Motion. Last product of the team, of course. Oh, sorry. I didn't see the images. So here we have several use cases where, for instance, here with these small pylons in American football, we use these small cameras in order to make a close-up of the touchdown moment in American football. So these pylons cannot be replaced by super slow-mo cameras because they would be smashed really often. So we need to use cheap cameras there. And in a similar manner, in NASCAR, we might want to film exactly what the pilot is seeing, or we want to film its reactions. And in the car, of course, there is no place for a super slow-mo camera. So our idea was to leverage video interpolation in order to create automatically super slow-mo replays. So this is a naturally supervised problem if we already have a super slow-mo content. And there are, in fact, several approaches possible. So either using optical flow, where you explicitly understand the motion in the images, or by using more direct approaches where you use a deep neural network that are able to implicitly understand motion and occlusions. So here in broadcast, we are in a very difficult situation because there are a lot of movement. There are often very small objects that are sometimes blurred. And these small objects, like a ball, can be very important in order to understand the game. There are a lot of occlusions, and there are quite often repetitive patterns which are problematic in order to interpolate because there is ambiguity about their motion. And of course, we require the higher resolution possible, so HD or 4K. So as you can see, with our algorithm, we're able to create smooth and beautiful replays on any type of camera, on any type of content. So next, I'll talk about deblurring. So in the broadcasting industry, we expect the camera operators to be able to produce under any kind of conditions, beautiful, interesting, not too blurred or too noisy, and of nice color balances images. So this is a very high expectation, and of course, it's not always possible to meet all these requirements. So we've been looking at enhancement strategies such as deblurring. And in fact, there is quite a nice synergy between video interpolation and deblurring, because high-speed cameras produce sharper images. And so if you want to mimic a high-speed camera, you need to produce sharp images. So you need to deblur your normal footage in order to make it look like a high-speed content before interpolating it. So here in this result, you mainly see, whoa. You can see the effect mainly on the circle pitch markings. So that's it for this effect. And now Olivier will explain the cinematic effect.
Thank you. Our current conclusion is it is actually possible. So if you want to simulate the depth of field effect, you need to think about the physics that are actually behind it. And by the physics, I'm talking about the effect of the lens of the camera. So any point in the scene that is currently not being put into focus is imaged as a circle whose size actually depends on the depth of the specific point we are talking about. So in order to simulate the depth of field effect, the primary information that you need to get from your image is the depth of each pixel. And of course, the other information that you will need is the object that you want to put into focus. This consideration leads to this high-level overview of the algorithm that we are using to simulate the depth of field effect. So starting from the input image, we use a monocular depth estimation neural network to estimate the depth of each pixel. And we have the usual conclusion here is that if you take state-of-the-art, off-the-shelf pre-trained algorithm, you get pretty good results. But if you want the best possible result, you need to train this algorithm on your footage. So, and in this case, we are talking about sport footage. To compute the object to put into focus, the current approach that we are leveraging is to use an object detection algorithm and to select the object that is actually the closest to the camera. It gives something that is, I would say, workable, but it is definitely something to be improved. And we are thinking here about leveraging, of course, silency, but also tracking, because if sometimes you have an object that is very close to the camera, but that leaves the camera and that increases its distance to the camera, well, what the camera operator would do would be to keep the focus on this object. And we want to simulate this using tracking techniques. This is pretty much it. Here is the current results that we are getting with this approach. So it is currently not a shipping product, but I hope that like us, you find these results very compelling and actually very encouraging to continue in this direction. The last use case that we will be talking about today is to use augmented reality graphics in the replay. So augmented reality graphics is something you are already seeing on television, but you are not seeing them live actually, because it needs manual works from dedicated operators in order to be generated. And our vision is that now with modern computer vision tools, we can automate the generation of such graphics to make them available within the push of a button. And I will show you today very early results that demonstrate that this kind of graphics can now be made fully automatic. This is actually a very fun project because it combines multiple computer vision tasks in order to produce a result that is actually very simple to look at, but that involves real-time camera calibration in order to take into account the motion of the camera, that involves object detection, segmentation, and tracking, that involves depth estimation in order to know which object is currently in front of the other objects, and that involves also rendering techniques in order to produce compelling graphics. The first thing that we have tried is to highlight the trajectory of the ball. We believe that it is actually a great storytelling tool for the director, because in this case, it highlights the fact that there is a player that changed the trajectory of the ball with its head, and maybe that was not so obvious without the drawing of the trajectory on the ball on the frame. Since we are able to segment the object, we can also have a different kind of rendering. Here, this is what we are currently calling within the department the ghost effect, where we print the segmented object on the frame in order to visualize the trajectory. It is personally my favorite, but it is not up to me to decide which one to put on it. But I like it very much. Here is a last example where we show that well, these kind of effects, they are great storytelling tools. So in the context of baseball, it is very useful to compare the trajectories of the ball on different pitch to understand the strategy that the pitcher is currently using. And with these ball trajectories, you can make it pretty obvious how the pitcher changed the trajectory on the ball between the two separate throws. That was the last use case that we wanted to show you today. So I hope, we hope that we have managed to convince you that computer vision is a great tool to maximize the quality of sport content that you see on television. And as you have seen, there are actually a lot of different applications that can benefit from using computer vision. If you try to work in this field, don't forget that expectations are very high because we are operating in a live context. Actually, operators do not have time to review the content before putting it on air. So you need your system to have a success rate of not 99%, but you need to target 100%. And to do that, I would say, our takeaway is that you need to leverage all the sources of information that you can think of. You need to combine redundant detectors when you have the opportunity. And even for the most widespread computer vision tasks, such as object detection and person detection, training on your own data is often mandatory. I hope you enjoyed our presentation, and if you have questions, we would be very happy to at least try to get a good answer.
right? You're showing the 9 by 16 frame, right?
Yeah.
Which, to my eyes, kind of look like you're basically like predicting where the ball's going to go, following it. Is there, are you, so you could train something that is like trying to make that prediction of the ball, or not train something, sorry, just like all the filters or something to figure out that sort of thing. Is that, you mentioned 2 techniques. Was one of the techniques kind of that, like let's always sit for the ball and predict which way it's going, or are you actually just using like a drone head still and see
Well, so the question is,
kind of like are you using like traditional like ball tracking like
yes, so
versus like some sort of saliency?
we are using both actually. So when there is a ball, we leverage a ball detector. And this is actually one of the most important sources of information. But we need the technique to also work on situations where there is no ball in the picture. And to do that, we use a silency detection neural network.
So, right, so the ball detector, right? But then I also feel like your algorithm was like smart enough to maybe figure out where the ball heading.
Yeah.
And so it's more like ball detector and tracking, kind of like a traditional technique for that.
Well, okay, so I see your question. There are 2 cases to consider for that. If you are working on what we call a clip, so for example, when you do a replay, you put an in point, an endpoint, and so it defines a closed video sequence that will be put on air. You can analyze the full clip and use some kind of trajectory smoothing in order to produce content that is not jerky. But so you don't need predictive techniques such as Kalman filtering to make it work properly. But in the case of a live operation, when you don't know where the ball will be heading, we definitely use Kalman filterings and similar tools to kind of predict where the ball will be in the next frames.
But like a common filter is going to think that the ball is going to keep going, but real soccer field would stop it, it'll go the other way and stuff. Is that okay, or is there maybe a network that's helping figure that part out?
The balance between the Kalman filter and the other metrics that we are leveraging is definitely tricky for those use cases. But there is no neural network that predicts the future location of the ball at the moment.
I think that's one very important source of information to consider also for this kind of application is the position of the players around the ball. So this is also very important to have a nice trajectory. And we won't use an algorithm that only track the ball. We noticed that using the player position around the ball is very important.
Do you use like a special camera or just 4K, 8K resolution?
We use off-the-shelf robotically steered PTZ cameras, such as the ones sold by Panasonic.
But like you were mentioning that you were using a state-of-the-art detector, like the one should be like really small. Can you comment more about, are you using like YOLO or something special for that?
The detector that you are using for the ball is YOLACT++, actually.
And you were also talking about that you were detecting some events. Like, are you using like human inputs or is like deep learning for detecting?
We are actually detecting the events from the metrics that we are computing. So the cinematic effect is not real time at the moment. It is still baking, I would say. So we tend to operate in a two-step manner. So we first try to get the result right, and then we optimize for real-time computation. But looking back, for example, at the video interpolation technique, we are getting computation times that are similar to those that we were getting 2 years ago for the video interpolation. And the video interpolation is no real time, so I have good hopes that it can be optimized using the usual techniques of quantization, pruning, and for all the usual approaches to make it faster.
Talk about this deep learning effect. So I'm always focusing on the human, and I used to work on similar product. So I'm always focusing on the human. There is some accessory in the human along with it, or at the same time. Are you also computing? Let's say I'm holding a bag or software or software object. Is it also getting captured as a silent object, or it's just focusing on the human? And sometimes there's a miss between.
But your question is in the context of deep learning?
Yeah, for deep learning, and which is like text estimation.
Oh no, the cinematic effect you are talking about. So your question relates to the object that we will put into focus.
So are you specifically focusing only on the human, or it could be any object that?
For the moment, we are focusing on the human, yes, but it is, I would say, an open topic. So it's open for discussion at the moment. So it is a project that you are working on right now. At the moment, we are focusing a lot on the depth estimation. And regarding the object to be put into focus, we detect objects, we select the object that is the closest to the camera, and then we put this object into focus. Yeah. We will work on making something more sophisticated in the future, but honestly, it's not done yet.
Can you comment on the complexity of automatic offside detection? How close it is to being an automatic substitute to the VAR officials in the likes of games?
So yes, so automated offside detection is a hot topic, I would say, in the soccer world. So you have very reliable detectors in terms of player detection, tracking of the limbs of basically every body parts, and you can leverage these to automatically detect offside situation. I would say candidate offside situation, because you will be able to detect that the elbow of one player is more close to the goal line than the defender, for example. So this you will be able to detect. But there is a subjective part to the offside rule, being the fact that you need to only consider the players that are participating to the action. And honestly, I do not believe that this is something that we can reliably detect automatically at the moment with computer vision. So you will warn the referee that there might be an offside, but the final decision will still be made by the human for a few years, if you ask me.
So it's an assistant tool and automation.
Yeah.
Are there any other questions? I think we have time for one more question.
Yeah, I was wondering, like you chose so many use cases and applications. I was wondering, are there any of them used in the real world, either for broadcasting purposes or for helping the teams to improve their training?
So your question is, among these use cases, are there use cases that are actually being used?
Right now, yeah.
Yes, so the video interpolation is a shipping product. The offside line is a shipping product, and the robotic camera steering is a shipping product. These are the three products that are currently on the market and that you can use in a real production.
And like most matches, do they use the steering of the camera, or do they still use
It's a mix of both. So that's the spirit of the product, is to add camera positions on a production where there are human camera operators. It's more point of view, but the purpose of this system is not to completely replace camera operators. And we are leveraging footage made by camera operators to know where to point the robotic camera. So the system would actually not work if there was no main camera operator.
And that's what we have time for now. So again, thank you, Olivier and Dan, for your talk. It's very interesting. So now we will continue to the first oral paper, which is SoccerNet tracking, multi-object tracking dataset and benchmark in soccer videos, presented by Anthony from the University of Liège. So just find your presentation. And
all right, perfect. All right. So hi, everyone, and welcome to our session on SoccerNet tracking, multiple object tracking dataset and benchmark in soccer videos. So my name is Anthony Choppa, and I'm a postdoc researcher at the University of Liège, well, obviously in Belgium. And I'm here today with my co-authors, so Silvio Giancola, Adrien Deliège, Le Kang, Xin Xu, and Yu Cheng, Bernard Ganem, and Marc van Roggenbroek. This work is a joint collaboration, as you can see, between so Baidu Research, California, the University of Liège, and Chaos University. So this work is part of our latest release of the SoccerNet dataset. So yeah, of the SoccerNet dataset that we've been updating since actually 2018. So we've had in 2021 a first release of new annotations with SoccerNet v2, then this year SoccerNet v3, and this work on SoccerNet tracking is actually the final data set that we released on this large-scale data set. So to give you an idea, we have around 800 hours of videos on all our SoccerNet data, and we also have millions of annotations that are related to action spotting, camera shots, to player detection, player tracking, obviously now, and player reality. So we also organize yearly challenges at CVsports and ActivityNet workshops in CVPR, and we announced some of the results yesterday for 3 of the challenges, and we're going to present later today, so at 5 p.m., the camera calibration challenge results. And we also have an extended talk on SoccerNet at 4:15. So if you're interested about that, feel free to come to these sessions. It will be later today, so 4:15 and 5 p.m. in this same room. So first of all, so why did we want to tackle the tracking task actually? So obviously, the first thing that comes in mind is because it can be used for highlights and statistics. Obviously, if you can follow a player, you can like estimate its speed and its performance during the game, right? So for coaches and also for like if you want to analyze the other player's team, it is a great tool to automatically do that. But it's not the only application that we can do. So for instance, last year we presented a paper with Florian from EVS that actually used camera calibration and player localization to help action spotting. So action spotting is the task of detecting the events in the videos. And obviously this information that you can see in the middle with where you can have the players and the camera calibration, that can help obviously to increase the performance of action spotting. And we hope that player tracking will also, like with the temporal domain added, will also add value and add the performance to that. And finally, like if we look a bit into the future, we are now starting to see these reconstruction in VR of simulated game, right? So what if I told you that instead of having a simulated game, you could actually be in the place of a player during a real live game, right? So obviously that would require also tracking. And so that's why basically we wanted to tackle tracking. And for the scientific research, it's also a very hype domain somehow. So it made sense to add that to our dataset. So to present the dataset just a bit, and I will go into the detail a bit larger. This is a multiple object tracking dataset in soccer. So we're interested in different classes that you will see later. And it's also a dataset that improves on previous tracking dataset with, for instance, the long-term tracking and the international competitions that we organize are a great way to benchmark the different methods and to have everyone compete on exactly the same data. So our data is composed of 12 complete soccer games from the 2019 Swiss Super League that were all recorded from the main camera. So why is that important in tracking? Because if you have these broadcast games that you have on TV, obviously you're going to have a lot of camera cuts between like close-up, main camera, behind the goal and stuff like that. And this is not something that we want, because if we want to do some long-term tracking, it's better if you have a continuous feed, obviously, of camera. So we were very lucky to get our hands on these 12 games that we were able to share, obviously. And so out of these games, what we did was, all right, if we had to annotate all these 12 90-minute games, it would have cost like something very, very huge. So we decided to select from 11 games, 230-second clips around key events. So the first step was to actually retrieve those key events. So we annotated like all events occurring during the game, and around like important events such as goals, cards. We had these corners, direct free kick and stuff like that. We extracted manually by selecting manually 230-second clips that we could annotate, but we didn't want to lose this long-term tracking data. So we selected the complete soccer halftime that we wanted to annotate as well, so that we have from start to end all players that are tracked, right? So now on the annotation part, we annotated everything with bounding boxes, obviously, as it is usually done for tracking. And we had this tool that came from Super Annotate, where basically you have these keyframes, and in between the keyframes that you annotate, the width and the height of the bounding box, as well as the position, is interpolated. So this allows to speed up a bit the annotation process, obviously, but we still have something around 90% of frames that needed to be annotated, because otherwise, like the players switch direction too often. So it didn't cost it didn't improve a bit like too much the annotation time, but it was a nice feature. So we annotated all tracklets for players, referees, the staff, that when it goes on the field, like the medical staff, and obviously the ball as well, which is very important, as we've seen in the EVS presentation just before. And we wanted this data to meet the SoccerNet standards in terms of data distribution and benchmark. And if you want to know what this is, we have our talk at 4:15, as I said. But basically, it's providing everything in a very simple manner that you can download it like with a simple line of code and directly test some baselines and stuff like that. So regarding the annotation format, we followed the MOT20 dataset for maximum compatibility between the two datasets, so that if you're working on one dataset, you can directly transfer it to our dataset. And this is just an extra feature, but we annotated the jersey numbers when they were visible. So if you're working on that kind of stuff, you can use our data, but it's not used for tracking. Now, this is a bit like what the annotation look like in a very simple scenario. I will show you a much more complicated scenarios a bit after, but as you can see, like the player and the ball are very well tracked, and the bounding boxes are very tight. Now, if we compare our data set to other common MOT data set, we can see that we are the largest in terms of number of sequences and in terms of number of bounding boxes, which is absolutely huge. As you can see, like 3.6 million bounding boxes. And we are the second one in number of unique tracklets with 5,000, and the number of frames as well, the second ones. As you can see, we are also the first multi-object tracking dataset up to this day. But I've seen that during this CVsports workshop, there's going to be another dataset with drone player tracking. So I'm very excited to hear the talk of the authors. Otherwise, on the properties of the dataset, So as I said, we have multiple object tracking with different classes. One difficulty is that we have this different sized object with the ball that's very small compared to the players. And also a nice feature on our data set that is not common in like pedestrian data set is that most people are dressed the same, right? So inside the same team, the people features are very similar because their jerseys are very similar. And so that's something very challenging for the re-identification of the same player, because the network doesn't have to focus on only the jersey, but also on the hair of the players or on the shoes and stuff like that. Now, we have this long-term re-ID requirement that if a player leaves the frame, like he left on the right and then comes back, he still has to be matched as the same ID. And this is not something that is usually done in tracking dataset, but for our targeted application later, like you need to see that it's still the same player, even if he left the frame and come back after a few moments. Now, in soccer, obviously, you have very fast motion and fast changing motions as well, which is very hard to track. Like when there's a shot, the ball like accelerates very fast. And finally, we have a lot of occlusion scenarios, as you can see here with the corners, right? With people passing in front of each other and so on. So all this, the aim is to push research in tracking further with a very complicated use case, actually. So let's now talk a bit about the two tasks that we defined. Obviously, it's still tracking, but we decided to separate it in two parts. So in the first part, this is the challenge that we organized this year. We provided the videos and the ground truth bounding boxes. The only thing that people had to do was to associate the different bounding boxes over time. So it was a pure association task, right? But for next year, we are targeting a more wide application of tracking where people will only be provided with the raw video, and then we'll have to do both the detection and the association. We didn't want to do the full stuff at first because we wanted people to get started easily also on the data set. And as you will see, they achieved like some very impressive results. Now, if we talk a bit about the metric, I will just give a few words about that. But basically, before, if you're familiar with tracking, it was the MOTA that was used. But recently, Luyten and his colleagues presented the HOTA metric, which is a better balance between detection and association accuracy. So as you can see here, in the first case where we detect one player for half of the sequence, well, obviously all metrics are going to be at 50%, except IDF1, but that's another thing that I won't talk about. And in the third case, where we have these 4 ID switches for the same player, we have a MOTA, so the previous metric that was around 97%, which is not very representative of a good tracking algorithm, right? If you have your algorithm that is basically switching IDs 4 times, well, 3 times, and you have 97%, it doesn't make sense, right? But the OTA metric is much more balanced between detection and accuracy, as you can see here. So our tracking challenge was presented, the results were presented yesterday during the ActivityNet workshop. As I said, it was a focus on association and the upcoming task. But I will still give you, it will be detection and association, and I will still give you the results at the end of this talk, obviously. So now, to help people get started on the challenge, we wanted to provide some baselines so that they can, you know, if they don't know tracking yet, they can at least try first a few common baseline and then just improve on them. So we tested 3 different state-of-the-art baselines. If you're working with tracking, you're familiar with them. It's Deep Sort, Fairmont, and ByTrack. I won't go into the detail because this is not the topic of this talk, obviously. But we evaluated these 3 algorithms on our test set, which is public, the test set. Then we have the challenges, which is private. And we compared it under the 2 settings, so with and without ground truth detections provided. Now, if we take a look at the results without ground truth detection, so the real tracking task, let's say, we can see that the results are not that good, right? And this can be explained, for instance, by the fact that these algorithms are not trained specifically for soccer. So just like Olivier said before, if you want better results, you should fine-tune the networks or to retrain your networks on your data. And so that's what we did for Fairmont, because the training code was available for this one, obviously. And we saw an improvement of the performance as expected. Now, we also tested it also in the same setup as the challenge this year. So with the ground truth detections that are provided. And as you can see, the result is obviously better, right, than without the ground truth detection, but it's not perfect yet, which shows that our data set is actually quite challenging, right? Now, if you're a bit like, if you take a look closely at the detection accuracy, you can say, like, why isn't it 100% with ground truth detection? Well, this is absolutely normal, and it's due to the algorithms themselves that in the association process sometimes drop out a detection that they believe are not that good, even though it's the ground truth detections. But the methods that were provided this year for the challenges by the participants actually solved this problem. Now, we also have in the paper a per-class analysis. I won't go too much into the details, but just know that basically the actions where there are less motion are easier to track, like substitutions, and the ones that have very high motion and very high clusters, such as corners and direct free kicks, are the most difficult to track for all of these algorithms. Now you can see here some qualitative tracking results of bike track without ground truth detections provided. I think in this one, yeah, exactly. And this is the results of the challenges. So I won't go into the detail of the first teams, how they did that, because they actually have a paper during this workshop. I don't know if it's on that, but I don't want to spoil them. But basically, as you can see, we go from 71% OTA to 93%, which shows that the participants really tackled this task greatly. And we had 12 teams in total and a bit more than 100 different submissions on the test and challenge sets. Now, as a conclusion, I wanted to recall a bit what we proposed in this work. So basically, we proposed the largest tracking data set for soccer videos, and we compared several state-of-the-art tracking algorithms, as you've seen. We also organized a challenge this year that participants have completely crushed. And next year, we will complete the tracking challenge with the long-term tracking sequence as well that was not used this year, so the 45-minute halftime. So this will be part of the challenge next year. So if you're interested in that, make sure to participate with us. So thank you for your attention. We have a YouTube channel where we post some of our work. So if you want to know more about the work we do in our lab, it's called ICAD Research, as you can see. And otherwise, all the data and the code is already available on GitHub. So feel free to just take a picture of the QR code. Thank you very much. All right. So if you have any question, we have, I think, a few minutes, right? Yeah. Yeah.
So is there any distinction between online and offline class? Because if you have an offline class that you can generally perform better than an online one, it has access to the feature as well. Is there a distinction between online and offline classes?
That's a very good question. Thank you for that. So right now, there's no distinction between the two, but this is something that is very interesting because if we want to have these statistics in real time, we need these online algorithms. Right now, it's not the focus on the first challenge, and it's not going to be the focus on the second as well, I think. But that may be something that we could distinguish actually. So that's a very good point. Thank you.
Came back after, let's say, 30 minutes or I don't know, 20 minutes. So this is doing the same.
Yeah, so usually in soccer, this doesn't happen because if a player gets out of the game, usually it's for good. So we didn't encounter this in our 12 games, but yeah, if this were to happen, I think it would be like a very difficult corner case, but that will be very difficult for algorithms to actually retain. Yeah. Yes.
I think that soccer players have like a GPS wonder if would you ever be able to use that, provide that, do you have access to that?
Yeah, so unfortunately, we did not have access to that, so we had to annotate everything manually here. That's something that we may have in the future, but without the camera, unfortunately. So we will have the track, the position, but not really the camera that films it. So one or the other. So we don't have a setup like that yet, unfortunately. Yes, exactly. We are in discussion to get this kind of data, but right now it's not something that we have in our hand. Exactly, maybe for version 4, yeah. Yes.
In the data set, do you have videos of wide angle shots where you see all the players all the time in the stationary camera?
Yeah, so we don't have these fixed shots like for a very long time, but usually at the begin, like during the kickoff, you know, the beginning of the game or when there's a goal, usually the operator like zooms out a lot and you can see almost the entire field. Usually, maybe not the goalkeepers, but yeah, at the beginning of the sequence, usually we have that, but we don't have like EVS, these very wide shots. Great, yeah, we can talk about that. Thanks, that would be great. Thanks. All right. So if we don't have any question, maybe you can move on to the next, or is it online? All right.
So I think let's move on.
Okay,
So,
great. Thanks.
thank you. Next, we have our second. Do you not have it here? Or do you not have sent the? We have send it to me real quick. It's a hassle to move all around.
Sorry, what was that?
Can you send the presentation to me real
It's a
quick?
little bit hard because this is Mac and this is Keynote. I don't
Okay.
think it's-
Okay. What do you need?
just the HDMI, and then I can share the screen.
Well, you need to go on to Zoom, and then I can let you share the screen there.
Yeah, sorry.
Yeah. So we just need to quickly swap computer, and then we'll yeah, continue. So can we? Can you have it on here, or do I need to move my computer? Yeah, sorry about that.
No,
So you have the HDMI here, so it's on your website, or?
yeah.
Awesome. And Zoom.
I guess I have to share screen as well.
Yeah, you need to share them soon. So, so it's your second screen, isn't it? Yeah.
Cool. Good.
Yes. So our next speaker is Paul from. Oh, sorry.
Yeah, actually,
Kashan from Adobe, right? And it's monotrack shuttle trajectory reconstruction from monocular badminton video. The floor is yours.
Hi, can you hear me?
Yes.
Okay, great. Yeah, so hi, my name is Ruixian Wang. I'm a researcher at Adobe Research, and I'll be presenting our work on monotrack, which is a method for reconstructing shuttle trajectories in 3D from monocular badminton videos. Before I start, I just want to thank my intern, Paul Liu, for all the hard work. He did this project while interning with me at Adobe and did most of the heavy lifting, but unfortunately, due to travel arrangements, he cannot be here, so I'll take all the credits. Okay, so badminton games are so fast-paced with some shots reaching over 250 miles per hour on a small court. Players use a variety of shot types, often with drastically different height variations, to confuse the opponents and to change their strategies and change the pace to attack and defend. So 3D trajectories of the shot is really important in badminton and can give tactical insights about the game and inform the audience of the game progress. However, the trajectory is not very easy to recover from a monocular video because the depth is just not there in the video. It's not necessarily clear by looking at this green arrow, for example, whether it's an offensive shot, a defensive clear, or a neutral drive. However, when you look at a sequence of shots, we can actually reconstruct the trajectories much better in our brain. And just look at these last two shots. You can certainly tell the rough arc of the trajectories and even get a sense of the speed and the angle of the shot. This is because we humans are so good at processing these camera perspectives internally. We have a feeling for the court layout, the player height, player poses, different parts of the court, and also about generally how gravity works to bring down the objects. And so from all these information, we can get a decent picture in our mind about the shots. So monotrack is built on the same premise. Our hypothesis is that by inferring these accurate court layout, player poses, and a good shot segmentation, we can actually create a good 3D reconstruction of the shuttle trajectory from monocular videos. So here's just a preview for the 3D trajectory reconstructed using our system. So you can see that qualitatively, it works pretty well. Okay, so a little bit more related work to place ourselves in the literature. There's a lot of work in sports video analysis. Many are focusing on specific components of different parts of the video, such as detecting a player detecting a player, detecting a court, or localizing certain actions, analyzing the strokes, tracking the balls, all these good stuff. Monotrack is built on top of many of these work. There has been work on synthesizing sports videos, for example. There's a paper in 2020, Vid to Player, introduced by Zhang et al. They built player-specific reaction models and use it to drive video sprites, so you can simulate on-scene matches, which is really cool. Soccer on Your Left, Tabletop by Ramatas in 2018, reconstructed a soccer game in 3D and view it in an AR environment. And there has been just a lot of interest in using NERV and other generative models to synthesize novel views of scenes and different humans and maybe sports. On the other hand, there has been a lot of interest in the HCI community to actually use these machine learning models to solve important user problems. And so, for example, for badminton, Shuttle Space and TiV are two systems that was introduced in 2021. Look at how 3D trajectories of badminton shots can help analysts form technical opinions and suggestions and improve game planning. However, the 3D trajectories they're using in these work actually requires human in the loop. So they have to do like a few annotations per shot. And so that's really time consuming. In contrast, our model is fully automatic and can complement these work. Okay, so at a high level, monotrack is made up of 5 components. We first do a court detection, 2D shuttle tracking, pose tracking, and then using all these information, we do a shot segmentation, and then finally 3D reconstruction. So let me start by the court detection. Detecting the court is a pretty well-studied problem, as you know, and especially a lot of the times in badminton, this camera is just stationary. So we built our model based on this classic model-based court detection algorithm that basically runs line detection and then do a combinatorial search to fit this known court layout and then minimize the losses. And this works most of the time. But we actually found that in certain cases, this algorithm fails because we pin down a specific step in this algorithm that classifies the line into horizontal and vertical sets. And this is using absolute angles, and that only works for certain camera views and really can cause slowdowns because of the complexity. So instead of classifying these lines using angles, we just formulate it as a bipartite graph problem, and then we solve it with a greedy approach. I'm not gonna go into the details, but we show in the paper that our method can outperform this established baseline in both speed and accuracy. We raised the runtime by about a factor of 40, and then we increased the accuracy by about 10%. But I'll just refer you to the paper. Another two building blocks for us is the 2D shuttle tracking and post tracking. For the shuttle tracking, we closely follow what is known as the TrackNet, which is an architecture designed to track badminton shuttles in previous work. This is a U-net-like structure that takes in a stack of frames to give the model temporal context before the decoder outputs a prediction mask. And we tweak this model a little bit and use distillation training to get better efficiency and slightly higher accuracy. We're at about like 89% accuracy for tracking. The post-estimation part, we just closely follow the recent work HRNet, which gives us a per frame prediction for all the poses. And then we filter and track the detected poses by using their on-court projections. And this is one of the benefits of like having different signals and modalities in one go, because they complement each other. And this simple approach works pretty well for poses. And for details, I will refer you to the paper. Okay, so now finally, we have the court, we have the shuttle, we have the post. Before we can do trajectory reconstruction, we need to segment the videos. So the idea is that a badminton game consists of points. And each point, players play a rally, and which consists of multiple shots. So the trajectories are much simpler if you actually look at the individual shots. So we need to first determine how to segment the videos into units of shots. And that is, we have to figure out who hits the shot and when. So although general action recognition is pretty hard, we make several observations about the badminton hits. So first, the hits often happen at certain corners of the court, like these like 6 hot spots that I draw. And then players are trained to have consistent poses when hitting the shots from a location to maximize, their output and be efficient on their energy use. And obviously, the shuttle needs to be near that location on the court. So based on these observations, we designed a network that will concatenate information from the court, the shuttle, and the players' poses, and then send it through a recurrent network to classify the hits. So each prediction leverages a 12-frame temporal context and outputs a 3-way classification results of who hits it and whether it's a hit or not. Excuse me. Instead of using these predictions directly, however, we perform an additional post-processing steps. The idea is to enforce several constraints that make sense for badminton and optimize the predictions. So the objective of this optimization is basically to maximize the confidence, the sum over the entire rally. And this S is the confidence output by the HitNet architecture. And then we sum over M shots, where M is the variable that you're optimizing. And tau is just a constant for regularization. And so then we enforce several constraints, including the hits should always be around 1 second apart. That's just the physical dimensions of the court and the speed of the shots. So it's the heuristics. Any 2 shots cannot be too close, obviously, because there's a physical distance that the shuttle has to travel. And the same player cannot be hitting the adjacent hits, because that's just the badminton rule. So this optimization problem can be solved in a dynamic programming in linear time, even though it looks kind of complicated. Okay, so here's the result of our HitNet plus the post-processing optimization tested on the TrackNet data set, which consists of about 200 rallies and in 26 matches. And so we outperformed 2 baseline methods that use just the derivatives of the positions and also a simple classifier trained with random forests. So this experiment shows that the optimization actually drastically improves the performance. And obviously using all 3 cues of the court, the pose, and the shuttle is pretty critical to the performance. This hits only happens sparsely in a game. So we actually balance the data set so that the hits and non-hits are equal number. Okay, so finally, we can talk about the 3D reconstruction of the shuttle. So the dynamics of the badminton shuttle just follows it's quite similar to what is known as particle under drag forces, which gives you some differential equations like this. So if you know, if you know the initial positions x0 and velocity v0 in 3D, then it's not very hard to figure out the entire trajectory. You just integrate this differential equation, you get the trajectory. And then once you have the trajectory, we can project it back to the image space and using the camera projection matrix that we get from the port. And then this allows us to see, how close is the current guess of the trajectory to the actual observation. And if we want the best trajectory, obviously we just have to optimize this loss. But remember, actually, we don't have the 3D coordinates, right? We don't have this x0 or v0 in the first place. So to find these, we turn this into another optimization problem. The objective of the optimization is to obviously optimize and minimize the reprojection loss, scaled by some constant, but also like we found it to be very beneficial to add some additional terms that says, the trajectories cannot deviate from the hitter or the receiver from at the beginning and the end of the trajectories. And also like we added a heuristic term to rule out, cases where the trajectory just shoot very far away from the court. So that's this like last regularization DO term. And we also added a few constraints that, just kind of make sure like the world doesn't go crazy, like the shuttle stays above the ground and the velocity doesn't, go above, speed of light or something. So those are pretty, let's see the paper for details. And then I guess like to evaluate the performance of this method, it's hard because we don't have ground truth. And so we first constructed a simulated data set that contains about 10,000 simulated synthetic trajectories. And then we injected some noise and run our method. And the average is shown here per zone in the badminton court, divided into 9 different parts. It's shown in centimeters. So the average error when using the full loss is about 8 centimeters. The racket of badminton itself is 65 centimeters, and we're not modeling those. So this is actually not bad. We also noticed some zone-specific loss, but there's a whole paragraph in the paper that describes and discusses phenomenon. Basically, it's about observation time, like when the shots are being hit from the front, you have less observation, and so that constrained the optimization and projection a little bit less well. And I will refer you to the paper for this detail. We also report the reprojection errors on 3 test matches, and these are there are 2 points that I want to make here. One is that even though when the pipeline is run end to end, meaning everything is predicted, we still get about 30 pixels of errors, which is about like 1/20th of the resized image. It's not perfect, but if you look at the qualitative results, it features like where the shot is going to, where it's coming from, and the general height prediction is pretty good. We can also reduce the error 3 times more if we bootstrap and use the ground truth labels for hits and shallow locations. And even though all these modalities that we presented are at about above 90% accuracy, the error in these like early stages is going to propagate and it's just going to accumulate downstream and affects the overall performance. So just like you said, 100% is pretty important. So here is just some additional results. What I'm showing here is just the projection of the computed 3D trajectories back into the image space. And so what you should expect is that I'm going to put a green dot on where we think the shuttle is, and it should follow the shuttle pretty well. I hope you can see the shuttle. Actually, I think it's a little bit hard to see the shuttle, so you just kind of have to take my words for it. It's pretty close. And there are a few shots where there are some false positives on the hit detection from the reflections of the rackets and other things, and that misguided the reconstruction, but overall it performs pretty well. Here's another rally from another match. Okay, and in this case, actually, the top of the net isn't aligned perfectly with the line, but the reconstruction is still pretty good. So it's kind of robust to those small errors. Here, I just want to show a few simple possible applications based on monotrack. So for example, here, I'm showing you a demo where we categorize each shot in a video collections and basically allows the user to retrieve the shots based on their annotations. And then here's another potential applications in immersive training using a reconstructed trajectories. I hope you can see it, but we're basically replaying the trajectories in 3D and try to facilitate training scenarios by raising the situational awareness. Okay, so in conclusion, we presented monotrack, which is a system for reconstructing shuttle trajectories from monocular badminton videos. We did this by first detecting the court, the pose, and the shuttle positions, and then solved the shot segmentation problem by using all these cues and a recurrent network. And finally, we formulated the 3D reconstruction problem as a constrained nonlinear optimization and leveraged strong physics prior. And there are some limitations and discussions. Certain models in the pipeline, especially the shuttle tracking, does not work very well if you don't have these like broadcast camera views. So that can be improved. Despite the hit detection is at about 90+%, it still has a lot of room for improvements. Otherwise, it will ruin some shots, just like I showed. We believe this technique can have provide deeper spatial information in badminton that can be useful for HCI and sports analytics purposes. That's it. Thank you. I don't know if we have time for questions.
A few, but we also had a coffee break afterwards. So
Okay. Okay, sure. Yeah. Is there any question? Yeah.
Can you elaborate a bit about like physics to get how complex are all of that? Shuttle, the physics is quite complicated. There's some drag,
Yeah.
How detailed was that model?
Yeah, so that part is actually based on previous work where they did a lot of experiments to show that this differential equation actually approximates the badminton shots pretty well. I mean, there's a lot of like crazy effects in physics. Like the badminton shots is actually made of, the shuttle is actually made of feathers, so it can compress. So that causes like nonlinear effects. And then like, if you do like net shots, the shuttle is actually not always pointing forward. Like it will like tumble a lot, and that causes like different change of the drag coefficients during the shot. What we did was a very simple thing, which is we take the drag coefficient, which is one of the parameters in this equation, and then we optimize it using data-driven approaches for each shot. So we have like an optimized parameter for each shot, but obviously that's still a model. Yeah. Yeah, so actually, that's a good question. I think the badminton is actually a harder case because compared to tennis, actually maybe that's not politically correct, but basically in tennis and table tennis, the ball is allowed to bounce on the ground, which provides the 3D anchor points of the reconstruction. But for badminton, the shots is always in the air, and players actually jumps a lot, and it's very fast, and like the shuttle is really small. So we think in principle the method should work on other racket sports, but obviously there are differences, and there are like spins and other things in tennis and in table tennis. But yeah.
No more questions. So now when we have a coffee break until 11 a.m.
Oh, I just want to say the last thing. So if you're interested in any of these, like talk to me about internships. I'm happy to chat with you. Send me an email or something. Thank you.
Good talk. Keep my cursor on. Okay. So I think we are ready to resume the workshop again. Okay. Everybody? We will resume the workshop again now. And we will start out with a keynote from Pascal Bauer, who is a what's it called a data scientist at CVsports Analytics, and also a senior manager of data science and machine learning for the German soccer national team. And the floor is yours, Pascal.
So hello everybody. Hope you can hear and see me, or at least see my slides, which is more important. I'm here as a kind of short-term replacement for Luke Bourne. I think Luke is somewhere in the agenda, which is always a tough thing, right? To trying to replace Luke. And my talk will be rather looking at applications from computer vision based data, or data that come from computer vision tracking, what you see in the title, right? So with the roles that Rike just mentioned, as a data scientist for the German national team, I'm kind of more on the practical side from a soccer federation perspective. And at CVsports Analytics, this is the company which Luke Bourne funded. I'm looking at tracking data rather from a club perspective, which are two different things. And I'd like to show you the overview in the upcoming talk. And the third thing I've done is I made my PhD thesis or my doctorate thesis on the detection of tactical patterns in soccer using tracking data and some kind of event data. And what I'd like to show you is, as I said, an overview of the applications, how tracking data are actually used in soccer. And then I'd like to do rather a scientific deep dive into the detection of tactical patterns within the next half hour or so. So the next two slides should actually be rather repetition for you, right? So what we got with any professional club or federation is tracking data. Here you see the tracking cameras installed in the stadium from Carnegie. This is what we used in the current contract period, so to say. So you got 6 cameras on each side of the pitch and 3 cameras behind the pitch, fixed, installed in the stadium, and on all these data, some tracking vendors, in this case, Carnegie applies computer vision techniques to get actually positional data. That is something you should know, right? Here's a little video of the positional data. As you see, they take the video and transform it into 2D information, so to say, the XY coordinate of players, ball, and referee. For the ball, we get a Z coordinate, which is then the height for players. Some vendors offer it, some do not yet, but it's definitely relevant information. Those data have a high frequency, typically in 25 Hz, and are collected in this case by optical data. But in theory, it's possible also to collect those data sensor-based, for example, using a GPS or an LPS system. We can talk later a bit about the shortfalls of this method and why we in practice that the players definitely prefer optical tracking systems. The second relevant data source for the applications we're going to show later is event data, or in US sports often called play-by-play data. I think this is also nothing new to you. We can define it as a log of ball action. So in soccer, as in many other sports, you got per vendor a dedicated match catalog defining any possible event, like a tackle, a pass, a shot, a yellow card, a red card, whatever. So those events are defined in detail, and then you got trained operators collecting those data manually. Some vendors say that it's semi-automated. Of course, there's some software support, but you can't believe how much manual process is actually behind that data acquisition. For example, for the German national team in the Bundesliga, we got 5 people collecting the data for one match. And also the example of a shot event, which is then the event, shows that there is not only the events and the player taking the shot taken, but rather up to 30 sub-events, which are called attributes, information like whether the shot was direct, whether it was a free kick, with which body part the shot was taken, and many, many more. So on top of those positional data, the event data give us valuable information that are used. And I think in one of the earlier talks, it is mentioned that automatically getting those event data out of the positional data or out of some video footage would be very, very helpful. So this is the introduction. Again, nothing of that should be too new to you. And the next slide is kind of an overview based on my experience, how tracking data and also those event data can help to improve performance in soccer. Again, both from a federation perspective, what is definitely different because we don't pay player salaries or market fee, transfer market fees, but also from a club perspective. And the first thing, this is the focus area of this talk, is that data can help us drastically, and I hope you'll be convinced after this talk, to support the processes in the everyday business, from experts working on the soccer side of things, for example, coaches, match or video analysts, and so on and so forth. So I'll show you some examples of that. The second thing, which we also use at a federation, is to objectively evaluate performance rather from a tactical perspective. So in soccer, as in many other sports, tactics kind of evolve based on coaches' ideas, things that just developed. And in many cases, new tactics kind of came up, new strategies, new tactics, and there is no evidence that they are efficient or not, right? So we're doing we spend a bunch of time into objectively evaluating strategies that are applied. This is the second major benefit of using tracking data in soccer. A third thing, which is definitely the focus of Zealous Analytics, where I work as a part-time data scientist in the company and funded by Luke Bourne, is that data are used to make fact-based scouting and transfer decisions. And as you can imagine, or as you know from other sports like baseball and basketball, there is a huge value in it because experts often wrongly estimate the value of players. And what Zealous is trying to do is to give each player kind of a dollar value and then make based on the data we got, could be either tracking or event data. Of course, tracking data would be more accurate, and based on that value, they build all their transfer market decisions. Again, from a federation perspective, that is not our focus area because we don't need to pay the players, and it's rather easy, I would say, for coaches to find, in our case, the best players in Germany. I think this is something human being can pretty good define or find or detect out of the set of players we get. But I think humans are struggling if you get the task to find the players with the best cost benefit ratio, right? So as you see, there are huge exhaustive transfer fees and salaries paid to the big players, and you sometimes can doubt that those are in a fair relation with the performance that the players actually can bring on the pitch. And the fourth area, which is quite relevant, but rather upcoming from a scientific perspective, so there is not that much work done yet in that area, is data-driven workload management. As you can imagine, we got those data tracking and positional data primarily for matches, but there are also ways to collect data from training sessions. For us at the national team, we got our players training with the clubs, then they're training with us, then they go back to the clubs, then we got matches for clubs and the national team, and so on and so forth. And we're trying to use all those data to have kind of a gapless workload profile of a player over the whole year to get kind of an alarm whenever a player's load is over what he's used to in order to prevent injuries or stuff like that, right? So this is an area where data scientists and sports scientists, so that whole workload management area before data, where there was rather in the sports science domain, are starting to collaborate to define metrics and to build algorithms based on the data, primarily basic tracking data, to detect when a player is in a danger zone to get an injury. Again, I would like to focus on the first part. So how are actually processes in soccer automated using tracking data? And what you see here is kind of the motivation for this. This is the workplace or the desk of a video analyst, which is installed in every professional football club. So often they got 2 or 3 analysts, depending on how big the club is, during a match. And what you see is they get live the video in a system, and they got the task, not only for their own matches, but also for the opponent, to tag repeating patterns of a match, right? So there is a pattern like a build-up play or a counter-pressing strategy or a high press of one team or a corner kick. So all those tactical patterns are manually tagged by the video analyst, for the reason that if the coach comes and says, hey, show me all the build-up phases of the first half, I want to choose one scene and show it in halftime, they need to be prepared and need to get this scenes ready. Again, for the own match, it's not that big of a problem because
Some
kind of a background noise. Okay, sounds good.
Please continue, Pascal.
Yeah. So this is rather a problem, or the effort is huge if you got to do this for the next opponent, or you got to tag the last 5 or 6 matches for each opponent. And as you can imagine, tagging always the same pattern again is a repetitive and exhaustive task. And this is kind of the motivation for the work I've done in my PhD. And this figure should show it pretty good, right? So at the end of the day, on the right side, you want to find scenes of interest. Let's call it tactical patterns, and then create playlists or reports for coaches so that they can look through one tactical pattern for an opponent or for the own team. And the traditional process is that match analysts do that based on video footage or live match manually. And what we were trying to do is to use machine learning algorithms and the positional and event data to get to those playlists automatically, right? So there's a huge practical need to support match analysts with this process, especially to help them automatically detecting the tactical patterns. And to motivate this a bit from a literature perspective, I found in my PhD roughly 50 studies on the detection of tactical patterns using some kind of data. Often there were no established definitions on frameworks. So what is a tactical pattern? That's the beginning. And how is a specific tactical pattern defined? So this is something missing across all sports. Tactical pattern detection has been an issue in multiple sports, whereas soccer has a huge amount because it's I would say rather one of the most complex sport. There are different types of data used. Some use positional data. Some approaches go the direct way from video footage, applying computer vision, and then detect the tactical patterns directly from there. Many approaches use event data, and only little approaches combine positional and event data, which is my preferred solution nowadays, because in both data sets, you get some valuable information that are missing in the other. And the method is, and I think that is clear, that you can either use supervised approaches where you need to label the tactical patterns in the beginning, and unsupervised approaches where it is the objective to take the data and find the patterns on their own, right? And the supervised approaches are kind of represented little in soccer. So this was another motivation for us to go that direction. The labeling process in case of supervised approaches is that we found only a little studies with a proper interlabeler reliability, which we think is pretty important, because you got those fuzzily defined patterns, and if you just label them, it'll be hard for an algorithm or impossible to detect something with an accuracy higher than the inter or intralabeler reliability would be. So from a literature perspective, from related work perspective, there is a lack of supervised machine learning approaches in soccer using the combination of positional and event data and integrating clear definitions and a rigorous labeling process. So altogether, the motivation, we got that huge practical need to support match analysts because they are valuable resources, and we should support them with those stupid, repetitive, tedious tasks and let them focus on the cool things and on the things where they're actually experts at. We got that lack of literature to do that using the specific methods in soccer, and that brought us in the PhD to the research question, how can tactical patterns be detected automatically using machine learning algorithms based on position and event data? So that's kind of the application. And in soccer, there are very established patterns of play, also often referred to as phases of play. And the basic idea behind this is pretty simple. You split the game into offensive, defensive, and since those situations are pretty important, you treat typically the transition situations, both to offense and to defense, as separate phases. And then there are other phases like when the ball is out of play, something where possession is unclear, and set pieces. And in each of those categories, there are subcategories like build-up play or attacking play in the offense. We don't need to go into detail for all of those phases. So there's the same for defense, transition to offense, and transition to defense. And one thing I'd like to show you, one part of my PhD is with the focus on counterpressing. So we started with that pattern and implemented a pretty simple method from a machine learning perspective to automatically detect a counterpressing pattern. To give you a rough idea what counterpressing is for the non-soccer experts, I hope that that video makes it clear. We're looking at the white team losing the ball, and we'll see two videos with two different strategies. So in the first video, the white team loses the ball here. And as you can see, they focus on defending their own goal, right? So they move backwards, they go into their optimal defensive position, they get compact and aim to defend their goal rather than directly trying to regain possession of the ball. In the second video, it's the same match, the same team. You see again the white team losing the ball, so we get transition to defense. And what you see is that the white players try to directly re-attack the ball. So they aim to directly put pressure, spatial temporal pressure on the ball carrier or the players around them to regain possession. To make it clear again, I'm going to play the videos one more time. So you get both transition to defense. And the task of our algorithm is in that situation to differentiate from this situation, that typical fallback and defend, to this situation, a typical counter press, right? With the objective to regain the ball immediately as close as possible to where the team lost it. You see two figures again of both behaviors, the dotted line. So there's a ball possession chain, ball loss of the blue team in those figures, and the dotted lines indicate the optimal movement in each of the scenarios, right? So, and what exactly the pattern is not that relevant for this talk. I just chose counterpressing because the method is pretty simple, how we try to implement it, and hopefully you see that the pattern is rather complex, right? So that it's hard to define rules to detect that pattern. So what we did is, luckily we had a bunch of students that labeled 11,000 transition situations with 3,000, roughly 3,000 labeled as counterpressing with a okay interlabeler reliability of 80%. As you can imagine, there are some situations where maybe half of the team is doing counterpressing, the other half is doing fallback. So you won't get an agreement for all situations, but 82% is okay. And from a method perspective, we started with two rule-based approaches as a baseline. Then we defined roughly 130 handcrafted features. We defined features at discrete time points. So we took the ball possession change 1 second and 2 seconds after to drastically reduce the dimensionality and kind of get rid of the problem that we get temporal data. And we defined those features for each of the teams and for the ball possession change setup in general. And then we just applied supervised machine learning algorithms. In our case, an extreme gradient boosting algorithms performed best. So that we were able to automatically detect counter-pressing situations for, I don't want to go into detail in terms of the results and stuff like that. I can only refer to the thesis, which is in the references, or the paper on counter-pressing for all details, or we can for sure clarify things in the question section later. I would like to focus rather on the application, where you see the figure on the right side that shows us that with our algorithm, the match analyst, the video analyst, doesn't have to go through 164 transition to defense phases, because our algorithm already drops out 134 situations where he's pretty sure that it's no counter-pressing, and says, hey, here are 30 situations which we detected, or which the algorithm detected as counter-pressing, where the analyst can go through before he presents it to the coach and say, okay, those 5 are kind of false positive, we kick them out, and he can get pretty quick to the 25 counter-pressing situations. And imagine this is only one pattern and one match. You can easily apply that algorithm to multiple patterns. We'll see that in a few slides. And you can easily apply that to multiple matches if you want to see a bunch of counter-pressing situations of your next opponent. Another advantage of data is, of course, that we can perform long-term analysis and see how efficient that counter-pressing strategy, which came up, I don't know, 10 years ago, kind of coined by Pep Guardiola and Jurgen Klopp, two famous coaches. And we can put some evidence behind kind of the efficiency and say, hey, it makes sense to do it in that situation, but maybe not in that situation, or it makes only sense to do that kind of risky pattern for a strong team and rather not for a weak team and stuff like that, right? So that is the application. From a machine learning or method perspective, there are obviously 2 major limitations. One is that the feature extraction, the definition of those 134 features, is pretty exhaustive. And even tougher is the problem that we needed students to label 11,000 counter-pressing situations. So again, also the labeling study that is needed for this analysis is pretty exhaustive and for sure a limitation. And what I did in my PhD is I started with counter-pressing, where we had those limitations and maybe the advantage that the features were interpreted, what actually helped. And we tried to detect other patterns with other methods where in a second step, we modeled the positional data as an image, right? So really as an image with the sizes of the pitch and the players for each team in one color channel as a pixel on that pitch filled actually, and the ball had a separate channel. And with that method, we kind of increased the dimensionality because the image was obviously sparsely filled. But we could use that modeling of the data, apply some CNNs in that case, which are pretty easy to apply to image data. And we could detect not only one, but in this case, 5 different tactical patterns with one and the same algorithm. The shortfall is that if you got all the players in an image, you lose kind of the orientation, which players who, and you're only able to detect team level patterns and not group level or individual player patterns. But we still had the shortfall of the exhaustive labeling process, which is something we try to overcome in the next study in the PhD, where we focus on set pieces and detecting kind of defensive strategies of players during corners, which is definitely then a group level pattern. For example, a player man marking another player, or player marking another player, or a player performing zonal marking, stuff like that. And what we did there is we applied a data augmentation methods and weak supervision to support that labeling process. So this was a first step to overcome that second limitation, namely the huge effort required to get labeled data in order to perform such a supervised algorithm. In the next study, we further worked on improving or overcoming that limitation by using, again, data augmentation as a helpful method, but then also variational autoencoder to support the labeling process. And to give you an example, whereas in the first study, we needed those 11,000 scenes labeled, in that last study where it was about detecting counterattacks, which is similar than counter pressing, just the other way around, right? It's a transition to offensive phase. We only needed, or we needed less than 50 scenes labeled, which changed kind of the whole setup and the effort needed to prepare such an experiment. And there are faces left that are not yet detected, but with that thesis, we tried to show that we can clearly define and detect tactical patterns using the position and event data. And we showed kind of a methodological improvement in terms of overcoming limitations of one study. Although the counter-pressing study itself kind of paid off in terms of the time we saved, right? So the experiment took us half a year or maybe a bit more to set everything up, but for every match, for every opponent analysis, we save our video, and there's so much time that it's kind of justified to spend the time into that experiment. And to get a bit more, to provide you a bit more details from a machine learning perspective, this is still not computer vision, but something that could also be interesting, is the evolution we made in terms of modeling those spatial temporal tracking data in order to perform such classification tasks. So in the first step, we had the feature extraction, which were defined features dedicated for this tactical pattern, so they are not that easy to reuse for different patterns. We were able to perform team level predictions, but we would also be able to perform player level predictions because we can define those features on a player level. Feature extraction is very effortful, but computing is pretty easy because the dimensionality of the feature space is rather low, even in our case where we had 134 features. And the second step, I think this was an idea introduced by Ulf Brefeld, is the representation of tracking data in an image. Again, you get an image with the size of the pitch, right? So it's 105x68 pixels. You use one color channel for each of the teams and the ball. And then you just fill that location of the player, that pixel where the player is, with a certain value. And the temporal information is included. That is something we introduced in our work, which I haven't seen before somewhere else, is including the temporal information by kind of a shading, right? So we took the last information on that sequence, or the information where the player was and the timestamps before, as kind of a shaded line in the picture. And again, this is pretty helpful because we get one representation that can be used to detect any kind of team level patterns. We're not able to detect group level patterns. And the shortfall of that is, and I think everybody who worked with CNNs knows that, is that it's computational pretty demanding. And I think it's not really efficient because we put data into a higher dimensionality in those sparsely filled images. And something we explored, or actually turned out to be pretty good solution for this approach, is using graph representations of data, which has the advantage that it has a way lower dimension. If you represent players and balls, the ball as node within a graph neural network, and any relationship between the player and ball as an edge. And the temporal information can be included within recurrent units within those graph neural network. And the good thing about that is that it's way more efficient in terms of computing than the CNNs, and that you're able to detect team level and group level patterns. And this is something we use to detect overlapping runs, which is a rather easy group level pattern. And that was presented this year at MIT Sloan conference, where we use those graph neural network representations to detect this tactical pattern. And this kind of shows a pretty, from my perspective, cool evolution of methods. And my guess would be that the graph representation of spatial temporal sports data in any sports will be the thing that you'll see way more often in the next years. And on the last slide, so as I said, that was rather a practical motivation for you to use computer vision to provide the practitioners cool data. And that you can get an impression how those data are actually used or can be used. And I think I'll try to link or kind of find the link between computer vision and the stuff that we do on the last slide. Obviously, anything we do is based on tracking data, and tracking data comes from computer vision. I mentioned earlier that it would, in theory, be possible to get the data from a match via GPS or LPS data. The issue is that players don't like to wear it, right? So you have no control if a player drops it in the halftime. You got no control over the opponent, right? So if you were the data, you were the GPS devices, then you can't force the opponent to wear it as well. And it is hard or not really established to have chips and balls as in other sports. So we really rely on optical data to optical tracking data to get an accurate data set from a match. Future work is definitely pose data and body orientation and also gaze information, right? So we reduce the position of players on a 2D image. Imagine that little video that I show, right? Soccer is complex and player movements and body gestures are rather complex, and reducing them to just 2D objects without knowing in which direction they're headed, their body is headed, in which direction the players look like, is definitely a limitation which would be interesting to overcome. And one thing that is pretty relevant in practice is to get data not from a sophisticated tracking system as shown in the video in the beginning from Karen Higo, where you get installed cameras fixed in the stadium, but rather to get those straight data from just TV footage or a single perspective footage, right? So we as a national team, we in the big competitions, the clubs get typically the data from all stadiums, because in any stadium in the Bundesliga or the Premier League or wherever, you got a tracking system installed and the data are shared across the clubs. When we play with the national team in the European qualifiers in Armenia or in North Macedonia, we get data from our own matches, but we don't get data from the opponent, which doesn't allow us then to do opponent analysis. So since it is pretty easy to get video from any match, not only professional matches, but also semi-professional matches, getting those tracking data from video footage is a very relevant task. The second thing, I tried to show you how effortful, exhaustive, and also expensive, if you want to buy it, the event data acquisition is. And I think there are a bunch of pretty cool approaches starting to get those events from video footage. And I think this will definitely also be a direction that can change the whole market, right? If we could get the events out of tracking data, things will get so much cheaper and easier. So this is definitely a relevant issue. And the last point, which I tried to show with the figures on the right side, what we do for the team meetings, where kind of our strategy, our tactic, or the opponent analysis is presented to the coaches to make it to the players, to make it easier for the players to understand our objective, is we animate those situations, right? So we highlight players, we highlight lines, we highlight spaces, and we want that in a fluent video or something like that. That makes it so much easier to give the message that you got to your players. And there are some tools that support that process, but I did it occasionally on my own, and it's still a very painful process, because at some point, if kind of that automated tracking loses a player, you got to manually draw his line to keep his animation in a fluid video. And this is something where computer vision can definitely also help to massively improve the process if those things are just provided in a cool tool way more smoothly. That's actually it. Seems like we're pretty good on time. Here are some references, and I'm very happy to answer your questions.
Thank you very much, Pascal. So if you have any questions here from the room, please go up to the mic so that it's easier to hear the questions. And I'll also monitor the chat to see if there is any questions there. Doesn't seem like there's any questions here. I would maybe ask, so you work primarily with the German national team. Do you need to somehow adjust the algorithm depending on different tactics, or is that entirely encoded, or is it like just entirely generalizable to different field position like configurations between teams, or is it a per team like network you're using?
So you mean the tactical patterns, for example, counter pressing, whether that is a general understanding of what a counter pressing is, or whether there is a team philosophy specific definition of counter pressing?
Do you adjust the methods so that they are fine-tuned per team in case the team has some specific approach to counter pressing or counter attacking?
Definitely. That's definitely the case. I think there are some patterns like a build-up where you got a pretty unified or generalizable definition. For things like counter pressing, we experienced that coaches see some things differently, right? And therefore it was so important after that first experiment to go to ways where you need less labeled data, right? With 11,000 labeled data, it'll be hard if a new coach arrives, as it happened at the DFB, who would have a different definition of counter pressing, to replicate that. Therefore, we aimed for methods where we use only little data. And if they got a new definition, right, we can just label 50 more data according to their definition and then retrain the algorithm. So it's definitely the case that you need to individualize those definitions of technical patterns.
Okay, cool. If there are no other questions from the room or from the chat, then okay, we have one over here. If you can go up to the mic, then hopefully Pascal can hear you.
Yeah.
First of all, please bring this text to West Ham. That's my first request. Waste of the German national team. Secondly, you mentioned you're doing some weekly supervised annotation on data. And one struggle we've seen a lot in the space is taking these massive clips and actually doing that kind of annotation at scale. Is there any more detail you can provide on how you go about that weekly supervised annotation process at the moment?
Could you hear the question, Pascal? Or
if you could repeat it, would be great. It was very hard.
I think that's maybe easier.
Okay.
The question I had was, you mentioned that currently you're doing some weekly supervised labeling on the long form video clips that you get of the games. I was wondering if you could give any more insight into how that works. It's a challenge we've had in the space as well.
So the first thing was the weekly supervised approach, or
yeah, exactly.
Yeah, I mean we use the Snorkel library, or I don't know if you heard about that, right? That was kind of a Stanford spin-off that provided some package where you can use those weekly supervised approaches. And the basic idea is that you define rules for your pattern to detect, right? And those rules, you define a bunch of rules, and then you can decide they can contradict each other. So for counter pressing, it would be, for example, if the team space gets smaller, then it is rather counter pressing. If the team center moves backwards, then it's counter pressing. So define 10, 15 rules for your pattern. And then you can do a majority vote or something like that if they contradict. And then you use the outcome of those rule-based detections of counter pressing as weekly supervised data, right? Obviously, they don't got 100% accuracy because you can't cover all the patterns by just rules, but they got some kind of information, or let's say an 80% accuracy, right? And then what you do is you use those weakly supervised data in combination with a smaller amount of manually, so more accurately supervised data. And then you train your algorithm using just less labeled data. That's how we approach it. That's the very basic version of how we applied weak supervision. The second question was
I think
data augmentation, or
I think it's you got his answer. But there's another question from chat asking if you tried using the raw data instead of trying to. So instead of performing feature extraction, modeling positional data as image or graphs, have you then tried using just the raw data for analysis?
I mean, the raw data would be the raw positional data, I guess, in that case. And the thing is, if you want to train a supervised algorithm, I think you need some representation of the data, right? So the raw data would be kind of 23 players with all their coordinates. You can't just throw that in an algorithm. So I think you need one modeling of those data to perform a supervised task. That would be my answer. I would have no idea how to throw the raw data into kind of an algorithm, right?
Okay, cool. If I know other questions, then I think we will continue to the next oral paper. And again, thank you for the presentation, Pascal.
I think there's one more.
Oh, there's one more. Yeah, sorry. How long in time/frames were your pattern sequences? Were the same length between 3 different approaches, features, images, and graphs?
Yeah, that's a good question, actually. For the counterpressing example, it is pretty easy because you can detect the counterpressing is something that happens directly after a transition, and we were pretty confident that it happens within the first 2 or 3 seconds, right? And then it happens or not. And therefore it was pretty easy because we could choose then those 3 discrete time points. For a pattern like build up or a high press or a high block or a mid block, you don't know how long that pattern lasts, right? So our approach with the feature extraction would definitely fail at that approach. Whereas if you just use that image representation, you can in theory analyze, or that's what we did, sequences as long as we want, right? You can do that by shifting a window through, but in theory you could analyze the whole match, and then for every frame you get your detection whether it's a build-up or not. So that will work. And for graphs, you're pretty flexible as well in analyzing patterns of different lengths. So this is definitely one cool advantage of the image representation and graph representation approach.
Cool. Awesome. Yes, I don't think there's any more questions now. But thank you, Pascal, for the interesting talk. Yeah. So I think we will continue to the next oral paper, which is post-tutor and explainable system for post-correction in the wild, which will be presented by Bat Ditkavi. So
thanks, everybody.
Just share the screen. Cool. Thank you.
Good morning, everyone. It's very cold inside, so I figured I should wear my full attire. Again, it's a sports conference here. And thank you, organizers, for making this workshop happen. My name is Bhat Dittakavi. I am a third-year PhD student from Indian Institute of Technology in Hyderabad in India. And I'm also a startup founder at Variance.ai. And the genesis of this work has to do with the startup goal of building a real-time personal trainer using mobile and deep vision. So that led me to sign up for PhD program at Indian Institute of Technology in Hyderabad. So here we are talking about, in this work, post-tutor. Post-tutor is about doing pose correction, human pose correction, that is exercise pose correction. All day we are talking about soccer and badminton and other sports. Today I'm going to talk about sports conditioning, and is about how would we stay fit, especially when work from home led to fitness from home. How do we have inexpensive systems that can be eventually used for us to stay fit? And using workout programs like yoga, Pilates, and Kung Fu and whatnot. So here we are having an explainable system for pose monitoring and pose correction using images in the wild of yoga, as well as Pilates, as well as some Kung Fu. Okay. Okay. So in summary, what we would achieve at the end of this work is that on the top row, on the left image, you see the correct poses. And here the poses are coming from either yoga or Pilates datasets. The top row is about, say, take the bow pose on the row 1, column 1. That is the correct way of doing it. Take the image below, and that is incorrectly being done. So the left knee is bent on the correct pose in the bow pose, versus the left knee is straight in the incorrect pose. So our system could identify the joint angle that is going wrong with the red circle. Similarly, in the second column, you could see in the half moon pose, again, the right way of doing this is the leg pointing the sky has to be straight. And if you see the incorrect version of it, the leg pointing the sky has the knee bent. So again, that bent joint is circled in red. So is the case with third. In the case of third, the left arm has to be holding in this camel pose the left ankle. However, in the incorrect pose, you see the left arm is pointing the sky. So the shoulder is at fault, the angle of the shoulder. So that is in red in color. So similarly, the fourth one, the scissors pose in Pilates, you need to have the formation of scissors between the legs. But the incorrectly done pose is both the legs are aligned. Again, the hip angle of the right leg is at fault. Our system is able to find that. So is the case with the teaser pose on the fifth, where the left knee is bent in the incorrect row. So to solve this problem of pose correction, first of all, we need to understand what pose is being done. When I say pose here, I mean it's a posture of yoga or Pilates, or it's a stance in Kung Fu. There is also another connotation in the literature of deep computer vision, is pose for the joint key points, XY coordinates of right shoulder, left shoulder, knees and elbows and ankles. That is called pose as well. So those are the key points. So when we say pose estimation, on the right side, we are talking about the problem of identifying the XY coordinates of the individual joints. So this particular problem that we are trying to solve, this particular task comes in between two well-known problems. One is human pose estimation. Like I explained in the rightmost figure, the person is running, you see those dots. Those are the joint coordinates. XY coordinates, this is 2D pose estimation. That is human pose estimation, the person running stance. On the left side, the person playing guitar, that has to do with human activity recognition, wherein we are trying to find out, given a very mini video of free frames, is a person playing soccer, is a person playing guitar. It is about recognizing the activity being done in that mini video. So our pose monitoring lies in between these two well-known problems. In pose estimation, we are only worried about getting those 17 or 18 joints and their spatial coordinates. When it comes to activity recognition, it is about recognizing the activity being done by the person or the subject in the video. But in pose monitoring, we not only have to identify precisely what the pose the person is doing, then we will extend the pose monitoring to pose correction. That is what is again another subject of interest in the literature. So first we need to do the pose monitoring or pose recognition, followed by pose correction. So here pose estimation doesn't give any emphasis on classification of the person's pose, whereas human activity recognition doesn't give detailed emphasis on what fine, refined pose the person is doing. It's only giving a generalized activity. Just to give you a peek at the 3 datasets that we have used, the first one, Yoga 82, is a CVPR workshop dataset paper that we used. And if you see some of the images, it is not that easy, especially when yoga poses have occlusions, self-occlusions, wherein one joint is occluding the other joint. So occlusion is a challenge. Even now, it's an open challenge. And we are dealing with such datasets. In case of Pilates and Kung Fu, these are much smaller datasets that we use some of the images from the open source scraping. If you see Yoga 82, it has 82 classes and it has around 21,000 images. If you see Pilates, it has 32 classes and around 2,473 images in total in this dataset. Kung Fu only has 7 classes and 179 images. Kung Fu being a small dataset, our performance on this dataset hasn't been that good, but other 2 datasets, you could see our performance in the later slides. I also have put together the distribution of these images by each class, by each dataset. So our key contributions are that we built an explainable, when it comes to correcting somebody's pose or posture, we need to make sure the vision model or any other deep learning model that is behind the correction and recognition is explainable by nature. If we only can understand how the model is calling a particular boat pose as a boat pose, then only we can bring explainability after that. That could be used to do the pose correction. And the second takeaway is that we have built a robust framework that could be applicable to multiple data sets as a framework. The third thing is that we also, any such system that we build requires experts from the field, from these workouts to come and validate our results. So we also have user study. That is a good takeaway from this paper. And finally, we are not manually annotating all these key points that we talked about. We are using off-the-shelf pose estimator, in this case, transpose. That off-the-shelf pose estimator is giving noisy key points. And we are using these noisy key points to the pose monitoring and pose estimation, along with combination of vision model as well as a skeleton model that you will see in the next slide. So any particular system that would do the yoga pose / Pilates pose recognition or classification of a posture needs to have some explainability inherently built within it. So we took pre-trained CNN networks. In this case, this is DenseNet, and try to see whether the prediction of a particular given input test image's yoga class label has any inherent way of looking at particular joint that is responsible for that pose. So we brought in visual explainable models such as GradCam++, Smooth GradCam++. And then if you see those heat maps on the left image, if you see the heat maps on the yoga poses, for all the different kinds of yoga poses that are getting predicted by this particular vision model called DenseNet, you notice that the vision model is looking at the entire torso. It is not looking at a particular body part or a few body parts that would uniquely identify a particular pose. So obviously this is not working. So vision model alone cannot do the pose monitoring for us or pose recognition effectively when your ultimate goal is to explain how the pose model is predicted, as well as use that data to do the pose correction of which joint is going right versus which body joint is going wrong. So what we have done in this course to find framework is that we have put together a framework wherein an image is given, a corresponding images is sent to a dense model, pre-trained CNN with with each and every data set in the question that we talked about, one at a time. And then the vision model is going to give us its top T predictions by the class probabilities. We take top T predictions. In this case, if you see this particular bow pose, we have taken the top 5 predictions. When you see the top 5 predictions, we see the corresponding key points from the training data, and those key points are having corresponding training data for these 5 predictions. And then we are using a skeleton model by limiting the training data for the skeleton model. In this case, we are using k nearest neighbors. The reason why we use k nearest neighbors is because it is inherently explainable. We can say, I am like you, I'm doing the pose like you're doing. This instance is like the other instance. Instance-based models in general have high explainability, and hence we picked, compared with other machine learning models, k nearest neighbor as an explainable model that takes the filtered training data from the top T predictions of the vision model. So we're using a coarse prediction using vision model, where it looks at the pixels of the data, which is one modality, and then we look at the key points generated from the off-the-shelf pose estimator, which is another modality. So that is we call fine prediction. So this coarse to fine prediction takes care of giving you a prediction, but that's not good enough. Now we know what class the person is performing, but we need to correct it. So for that, we used, loosely calling it likelihood, a likelihood mechanism. This is simply based on binning the distribution of the joints for a predicted class from the training data, and for that each of those angles and their angle distribution from the joints, we are calculating this angle from inverse cosine similarity, and we are looking at that angular distribution and then finding out given test image and its corresponding, say, shoulder angle and its corresponding training shoulder angle distribution, and see whether this particular angle of the person performing coming from the training data distribution of that particular angle or not. What is the likelihood that it is coming from the person's corresponding predicted poses, training data, angle distributions. And finally, we will rank order the predictions or likelihoods for each of these joint angles. And we say, you know what, these are the top n angles or the joints that maximally explain a given pose. If a particular angle, just in case, is not at all explaining a given pose, that could be a challenge, and that could be the angle, joint angle, that is incorrectly formed by the person. So that is where the lady performing the bow pose, the left knee is kept straight. That knee angle, when you look at it, that is having the lowest likelihood. So if you look at the pseudocode of this, I mean, this is pretty straightforward. During training, we have trained a DenseNet classifier on Yoga 82 dataset using a vision classifier, and we take off-the-shelf pose estimator, in this case transpose. We're just doing the inference of the key points, the 17 key points, using a pose extractor. Then what we are doing is we are generating joints for all the training data, all the key points for all the images in the training data using this pose extractor. Then once we have these key points, then we have many levers to play with. From the key points, we could generate joint angles. If you have ABC, you could do inverse cosine similarity joint angles, where ABC are the 3 different joints. And you can generate the stick lengths. Maybe, who knows, the distance between one joint and the other has some correlation with what is a right pose versus wrong pose versus what pose it is. So we look at stick lengths. We also looked at the areas formed by these angles. So we have multiple ways and multiple levers to look at it. Later on, we did the ablation study. We figured that the best performing model has to deal with pose vectors. We are calling all the combinations of either key points or the angles or the stick lengths or the areas. These are all called combinations of these elements. We are calling them as pose vectors. So those are the pose vectors. There you see KNN vectors. So we generate these pose vectors. We figured the key points, XY coordinates plus the corresponding angles. The combination of these elements make the right effective, efficient pose vectors. So that KNN vectors have led to us finally at the test time, using the framework that we defined before, arrive at not only identify the right pose for that, as well as where the wood joint is going wrong. And here are some experimental results. And if you could see, the right side ablation study shows that joints plus angle combination as a pose vector is performing better for KNN or any other machine learning methods for the fine prediction. We have taken KNN intentionally because it has the highest explainability compared to random forest or naive Bayes or any other models out there in the classical machine learning side of it for the skeleton model. For the vision model, in this case, DenseNet that we used, you could see that 2 out of the 3 datasets have performed really well in the combination of DenseNet with k nearest neighbors. And this is the usual study that we have done. We have shown some random pictures of our predictions and then have experts, 12 yoga experts, 1 Pilates and 2 Kung Fu practitioners to come and say, what do they think about our predictions? We also asked the experts which of the 4 or 5 joints of the total 8 angles that we are looking at are formed correctly according to them. So our results under user studies, if you notice, have been in conformance with the experts' performance, especially we are looking at binomial statistical testing, and they seem to be in alignment with what experts are thinking in terms of our system's predictions. And when it comes to particular predictions on individual joints, our approval rates are 85% from the experts for yoga 82, 80% for Pilates, and 63 for Kung Fu because we are training it on very small data set. And our key takeaways, like I said before, we could take noisy key points. We don't necessarily need the real labeling and annotation, which is painful and time consuming of these data sets. With noisy key points coming off of off-the-shelf estimator, using 2 models, one is the vision model, the other is the skeleton model. The combination of this under a framework that we call coarse to fine framework, we could do the pose monitoring on top of it using statistical methods as well as using likelihood mechanism. We are able to identify the wrong joint or the joint that is going wrong when a user performs, so we can do the correction. Any questions?
How do you think this would generalize to other sports that are not stationary?
Definitely. I mean, if you have stationary sports where you could see the pose the person is performing, certain poses are very important. For example, you are doing wrestling, for example, and there are certain tactics you would have. When you have these tactics, and if you know a specific tactic would have a specific joint, a specific posture, and then specific joint angles it would come up with. So we could correct the right way of doing wrestling because now we have these joints, and that information could be very valuable in static sports, like you mentioned. Static in the sense, camera doesn't have to move. You're doing it in a bout, in a ring. Any sports where you do such things, even gymnastics, you could assess to the finest level how a particular pose or action happened through a series of poses effectively and efficiently, because that efficiency is important to gain the height or the length in gymnastics, for example. So definitely, yes. Thank you.
Yes. So the next oral paper is FenceNet, fine-grained footwork recognition in fencing, and it will be presented by Kevin. Yes. For sure.
Hello, everyone. I hope everyone is doing well. Thanks for having me here today. Everyone can hear me? Good. Yeah. So my name is Kevin. I'm a PhD student at the University of Waterloo, and I spend most of my time thinking about sports that I don't play. And today I want to share with you guys early stages, like results from the early stages of a project that started earlier this year at the Motion Research Group in collaboration with Fencing Canada and the Canadian Sports Institute, Ontario. Yeah, I wanted to mainly share some of the problems we have when applying computer vision to fencing, to make coaches happy, getting them what they want, etc. So kind of like a therapy session for me, right? Yeah, that's my introduction. And these are my co-authors, my supervisors, Professor John McPhee and Professor Alex Wong. And let's get started. So some of the things we're interested in, so technique retrieval, which involves action detection, segmentation, and classification. And also we know markerless motion capture results aren't super accurate. So the computed metrics from markerless mocap probably won't be. But if after processing, there is still good separation of these, I guess, inaccurate metrics between groups of athletes, we can still probably use them as proxies to create performance benchmarks, right? Which are useful in athlete selection, as well as monitoring, training, and progression. And this is something that CSIO is interested in. And for FenceNet, I want to see how good action recognition is in fencing using just pose features, or in this case, like really bad pose features, as you'll see soon. For example, in Saber, the coach is interested in detecting actions that occur in the first 3 to 5 seconds of the start of each bout, because these actions are usually premeditated. So tracking and analyzing these actions are useful for tactical planning. And right now, we're still in the process of data collection for both action tagging and mocap. And tagging fencing data is actually one of the most difficult parts of this project, at least so far, especially if you're like me and you don't really know much about fencing. So for this iteration of work, I took a publicly available data set called the fencing footwork data set. Which contains about 650 observations of 10 fencers with varying skill levels, and they perform 6 types of footwork actions for about 10 to 11 reps each. And since the fencing footwork data set, or FFD for short, they provided this 2D skeleton data, so we can kind of omit the pose estimator step. So it looks like this now. And so now at this point, you're probably going to say, oh, it's easy. It's just a classification task, right? So, and yep, that's why I did it. Well, to be fair, like the authors didn't upload RGB video, so I didn't have that to work with. They did upload depth videos, which look like this, which isn't very pretty. I overlaid their 2D skeleton data, so hopefully it helps or looks better. So I didn't show the stepping forward and stepping backwards motions because they're kind of just straightforward. There's 4 types of lunges, as the name suggests. It's like top left, the incremental speed lunge, the fencer incrementally increases his or her speed, right? And there's a faster one called the rapid lunge and a jumping sliding lunge where the front foot jumps forward and the back foot slides. And a with waiting lunge on the bottom right, which there's a short pause in the first stage of the lunge. So for example, in the top left and bottom right, the incremental speed lunge and with waiting lunge, they look pretty much the same, right? The incremental speed one is just slightly smoother and the other one has like a pause. And just going over the original author's method and as well as the data a little bit more. So the original author, essentially, they created 4 types of handcrafted features. So that's why I call it JLJ, to combine these 4 features. And they have their own, they propose their own feature selection method and their feature fusion scheme. And going back, I use the TCM-based network. So a quick review, TCNs are mainly comprised of causal dilated 1D convolutions. So causal as in, for each time step, you only retain information from previous steps and you can't look forward. And dilations are just introducing gaps between time steps. So for regular convolutions, that the dilation factor D is just 1. And so in comparison, I'm essentially using a deep learning approach, but only using the 2D skeleton data. Whereas like the previous author, if we go back, I guess, use the depth data, I'm used data and the 2D skeleton data. And then, yeah, just some like advantages or why I'm spending time on this. Using skeleton data allows us to bypass the need for physical sensors. So this is kind of main reason to do this. Other 2 advantages are basically advantages of deep learning, right? Having a larger receptive field and the simplicity and automation part. And jumping forward to results. I mean, since we're essentially comparing deep learning to handcrafted features, so it's not super surprising that they're pretty similar in results. FenceNet does almost as well as the original author's method. And we see that for both incremental speed and with weighting lunge, they don't perform as well. Like those 2 are the groups that have the most trouble. And a small modification I made was to incorporate the reverse direction of the movement, sort of like in Elmo, the language model, and where they looked at both directions of a sentence. So I just added another network, an anti-causal network I called here, which just takes the reverse action. And then, yeah, the outputs are concatenated and then fed into dense layers for classification. And so this improved the results a bit and now is better than the original author's method, which is nice. But one of the things I wasn't sure about was the bidirectionality part. So another paper I found that used something similar from Sun et al. So this was a structure I saw. And if you combine two directions of 1D convolution layers or 1D causal layers, I'm wondering if it's almost the same as rearranging regular convolutions in a way. So I just ran some experiments and investigated the direction or causality we call here. Comparing BiFenceNet to regular convolutions, BiFenceNet does do better. Also try using 2 networks with both forward directions of the motion with different network parameters and using just a wider version of the model to check if the improvement is just due to like a bigger model, being a bigger model, but it seems BiFenceNet still outperforms these other cases too. And I also plotted the results. So I computed the features, or I compared the features from BiFenceNet and regular convolutions. I took the features before the dense layers and reduced their dimension using UMAP. And it's not super different, but from the left or I guess the image on the right, your right, you see like a chicken feet kind of thing. And it appears there's better separation among the classes, especially the core sections, the stepping forward and back. And the lunges are kind of lumped together. Whereas on the CNN features, it's less apparent, I guess. And then jumping forward to some of the issues we have with the current iteration. So I suspect there is some mislabeling of the data, but this could also be due to like athletes misinterpreting the actions they're supposed to perform when collecting data, since they are of like different skill level. And another thing we care about is how well our method transfers to competition videos. Just looking like the first part, like quickly looking at the mislabeling. So in the jumping sliding lunge, the back foot jumps or will slide forward and moves. Whoops, sorry. And in all the other lunges, the back foot is pretty much stationary, but on the top right, you see a lunge where the back foot slides forward when it's not really, it usually shouldn't, and it's labeled as incremental speed. And this one, the bottom right, you see this being labeled as jumping sliding, and the back foot is still. So I checked these with the coaches, and they also agreed with me here, which is nice. And like with the competition setting, what if you watch an actual fencing competition, you'll notice that the actions are a lot more dynamic and complex in terms of movement. For example, if you tag it according to the previous directions, almost all the lunges are going to be jumping, sliding. Like coaches won't tell you to slow down during a match, right? So some, like if we're using this for competition, some modifications of the descriptions of the categories are probably needed. If like looking at another example, even for the course actions, such as stepping forward, in competition on the third GIF, you see that it might even resemble more of a jumping sliding lunge than the step forward from FFD. And yeah, so another thing I did at the end, if you kind of have too much time on your hands like me and you wanted to see what happens when you put a off-the-shelf pose estimator onto the ugly depth videos from before, I did that for you here. So I use Kapal. It's a single stage multi-person 2D pose estimator. So it might not be the most suited for this, but this is also work from our group. So I wanted to give a shout out to Will McNally and also Kanav in the back. And this is what it looks like. So it looks actually pretty good here without any like fine tuning of the model. This is just inference from Kapal on the depth video. And then, but there are some cases where it doesn't do that well. So for example, here where it skips a lot of frames, and I did tune the parameters quite a bit to try to get good results. And it's hard to do inference if, I mean, interpolate if a lot of the keyframes are skipped too. And if we look at the joint angles for pose estimation, the pose estimation results are obviously a lot messier than from Connect. I plotted the median, which is the line, and then the 25 and 75 quantiles. Yeah, but if we do the same as before, it's actually not that bad. So I only took 4 fencers versus 10 because for 6 of them, like there was just a lot of missing frames, and pose estimation wasn't able to capture a lot of the poses. And yeah, it did pretty well. It did surprisingly well. I also tried to see what happens when you train on the connect data and then test and predict on the 2D pose data extracted from Kapal. And yeah, it did better than I thought. And that's the end of my presentation. So with the connect data, so this is from the data's off like from a previous study. So yeah, I just took that, and I think it was like a pretty old version. It's like 2015-ish. Yeah. So it doesn't look really pretty. Oh, so we're still collecting a lot of data for both. We're both tagging a lot of competition data. It's really hard because in fencing, the actions aren't really black and white. And and so we're working with coaches to do that with help from them. And we're also collecting a lot of like mocap data from fencers. Like we're using like Vicon and different systems.
So in fencing, you have these 3 different kind of genres, like competitions. Are there any differences between poses? Most like the saber, the bow, and are there differences in the poses?
Like in terms of poses or?
Yeah, like in what the lunges that we use, how they are performed.
Yeah, so there are, but it's like hard for me. Like it depends really on. There is definitely differences in like techniques, but yeah, it's really we try to get feedback from coaches and see what they want to, what's important to them, what they want to extract.
It doesn't seem like there's any questions from chat, so unless we can go to lunch. And just before everybody goes to lunch, I would like to repeat what I said in the morning, that please put up your posters in the break so that we don't have to spend time in the poster session. And it's at, I believe, 187A to 208A. They're down in front of Hall D and E, and let me just double check the numbers. I had them here before. Yeah. Just yeah, so let me just find it here. Yeah, 187A to 206A. That's where you should put up the posters. Cool. And we will the workshop will return at 1:30. Cool.
Okay, thank you very much. So we're coming through okay on Zoom? Yeah. Well, as mentioned, my name is Patrick Lucy. I'm Chief Scientist at StatsPerform, so delighted to be here today. What I'm going to go through today is just our perspective in industry on how computer vision tracking is used in sport, and really focusing on a couple of key applications. So let's see if that can go through. Okay, so in terms of the overview, first of all, I'm going to go through the tracking landscape, so give a bit of history, and then talk about the different types of sports data that are used and the role of computer vision within that. Then I'll go through the applications of using computer vision tracking in sports, really from an industry perspective, and breaking that down into two buckets, precision applications and also scale applications. Then I'll focus on some of the trends that are happening in computer vision and how we can utilize that really around multi-sensor fusion and how we can really leverage human vision, because in sports, the best computer vision system out there is currently humans. And I'll go in a bit more detail there and how we can link that together. And then at the end, talk through some of the work that we're doing in broadcast tracking. So people don't know who StatsPerform. If you follow sports, you probably touch us every day. So wherever sports data is consumed, it's more often than not, we provide that. So if you Google a soccer score, Google gets their data from us. If you ask any sports question from Amazon Alexa or Apple Siri, that data comes from us. I'm sure if you follow soccer, you've heard the brand Opta. Opta's under StatsPerform. All sports books use our soccer data. A lot of teams around the world use our data as well. And so that kind of gives you perspective of what we do at StatsPerform. So again, if you haven't heard of us, I'm sure you touch us every day if you have anything to do with sport. Now, in terms of the history of sports data, in terms of sports innovation can be tied to sports data. And so Stats Inc., which was the first company, and then we merged, we had a couple of acquisitions, now we're StatsPerform. But our company got formed over 40 years ago And so that person there on the top left, Bill James, so he's basically come up with all the metrics that Billy being used in Moneyball. He was actually part of the grassroots movement that helped create Stats back in 1981. So John Dewan set up Stats Inc. and really their goal was to get better baseball data to come up with metrics. Daryl Morey, he actually started his career at Stats back in the mid-90s. He created a lot of his basketball metrics. Then he went to the Houston Rockets and then obviously at the 76ers. Now, in terms of soccer data, we've actually been collecting tracking data since 1999. People think that tracking data is a new thing. It's actually not. A couple of companies that we've acquired, Prozone and Misco, they started doing that back in 1999. Now, that was done by humans, okay? Then Opta in 2005, we first started generating live spatial locations back in 2005. And Running Ball, which is what provides all the sports books live data, and they have humans in venue, and we cover that for 100,000 games of soccer a year. We started doing that in 2006. So now in sport, the big thing, especially in betting, is around live player props, and we really fuel that. Now, then something happened in 2010. We started collecting ball and player tracking data via computer vision system. So this is our sport view system. It started being in the NBA in 2010, where we had 4 NBA arenas. In 2013, it went NBA wide. And so I like to call this the start of the AI, the AI period. So beforehand, we have the data-driven period where it was shown if you use data to make decisions in sport, you can do better than just using gut instinct. 2010, we started collecting more granular data, and that ushered in the AI or the V2 era. And really the motivation behind that was, well, we know the value of using data in sport. So we want to use computer vision to actually generate more granular data. However, this data is unstructured or semi-structured, so we really had to use machine learning to actually get in a form where we can actually utilize it. Now, in terms of sports data, we have to think about what's the value of sports data. And the way that I like to think about things is in terms of reconstruction. So you think about the value of sports data, it really reconstructs the story of the match. The more granular the data that we have, the better the story that we can tell. Now, in terms of the types of stories that we can tell very, very basic stories. And so we have box scores. So if you go to Google One Box, I have a 2-year-old daughter now. I haven't got time to watch a game for 90+ minutes. So within 5 seconds, just using box score data, which will give the score and maybe the time of goals, I can have a quick summary of what's happened there. Then we have play-by-play data, which gives us a description of what happens at the end of every possession. We can get a bit more granular by having spatial event data, where we can actually track all on-ball events for soccer in this situation. In basketball, we can look at shot locations. But really, the best data out there, especially when we're looking at match performance, is player tracking data. However, the kernel of all knowledge normally comes from video. So that's the foundation of all the data that we collect. Now, this is a computer vision conference, and really the first success story of a commercial computer vision system happened back in 2005. So when we started collecting ball tracking data. So Hawkeye had ball tracking data for tennis and cricket. It's used for officiating. In 2012, they had it for goal line technology. And then I mentioned it's evolved into player and ball tracking data. So here we had an in-venue solution where we had 6 cameras and we're able to track players, the XY location of players and the XYZ location of the ball and the XY location of the umpire. And we're able to do that 25 frames per second. More recently, we've evolved our technology. So Second Spectrum now are the data collectors in the NBA. We've evolved our technology to be more lightweight. So here I'm showcasing our SportView 2.0 solution, where we have 3 4K cameras. They're in a single view. We have a gaming machine there, and we're able to collect player tracking data and ball tracking data live. And this is enabling us to get us this player tracking data. Now, when people talk about player tracking data, people think this is big data. It's actually not. Video is big data. So if we have a video here of our in-venue solution in basketball, you have to think about what is the value of computer vision. Computer vision basically compresses what we have there in pixels down to these dots. And if you think about the level of compression that we have, So just say we have a single frame and we have 6 cameras and it's uncompressed. That's basically 300 megabytes per frame, right? Now, if you look at what we get with tracking data, we can basically compress all that down into 456 bytes. So it's close to 1,000,000 to 1 compression, okay? So that's what tracking data does. It compresses what we have in the pixels. And the nice virtue of this tracking data is that it's low dimensional, but also interactive and interpretable. And it enables us to do a lot of these things. The key thing with tracking data, though, is getting the right representation. The last 10 years, we've done a lot of great work getting the right mid-level representation to deal with these trajectories. But when we talk about tracking data, it gets it in a form where we can utilize it and compress, and we can do some really nice things. Now, obviously, this is evolving. We're looking at body pose. So we've used open pose extensively for a partnership with Yasser's group, and we can get more granular data, but still it's far more compressed than what we have in the raw video. Now, if you see how these systems have evolved too, if you look at baseball, Hawkeye have a computer vision based system. I think they use some radar information there too, where they track, you know, the ball at a very high frame rate. They're actually able to get the body pose as well. They actually look at the officiating. So after every match, I think there's a Twitter handle that looks into how accurate the umpires were. And so this has been used to pretty good effect. And so I like to call this data public data. I like at Stats Perform, I call us the keeper of public record. So when matches are played, we capture that data. And in terms of sports, this is really the primary data out there. Now, there are other forms of data out there, such as private data. So if you work for a football club, they have self-report, they have medical information, they have contracts, they have wearable information, but also in terms of computer vision, they have other systems. So in basketball, they have the NOAA system where they have a depth camera and they're able to track every shot. More recently, in a lab setting, they're able to look at the body pose of basketball players and looking at their form when they're shooting. I think that second one's from Mint, who's based out of UT Austin. And then if you look at Drive, I think it's Drive Arm or Drive Line, which look at the reconstruction of pitches. And so within in-lab settings, we're able to capture this very, very granular data. Then of course you have video games where you have the Vicon suits where you're able to capture very, very detailed data. However, this is problematic coming up with large scale solutions because it's private. And so mostly in the elite sphere, we look at public and private data. However, in the amateur space, there's a lot of great work happening, especially in terms of computer vision. So if you look at Home Court, they have a really nice offering where they can do shot analysis and just basketball analysis off your phone. Swing Vision, which can do similar for tennis. If you're looking at home health, connected health, look at Tempo. Via their mirror solution, they're able to give you feedback based on certain techniques when you're just exercising. And then if you're looking at automatic broadcasting, you have Key Motion, you have Pixelot. Excellent talk this morning, looking at how you can use that to augment top tier broadcasts. But at the lower tier, you have solutions there which are generating those outputs. So in terms of a canvas and how you can think about, we can apply computer vision technology to sport. This is, in my view, you know, the 3 tiers, and really what we look at Stats Perform is the public data. And so I'm going to go through how we can think about the value and still open challenges within the public data, especially around tracking data. And the way I like to think about it is you can think about applications in terms of 2 buckets. The first one is around precision and scale. However, we have these various forms of tracking data. So you have in-venue solutions, you have various computer vision tracking data. You do actually have other forms of tracking data. In the NFL, they have RFID, where they're tracking those players at a very high frame rate. However, it's not only just vision. So when we're looking at this data, we're always fusing in the human generated data, and it is very much a fusion problem. And so once we have that, the first step that we have is mapping those pixels to trajectories. And from those trajectories, we can drive a lot of outputs in these 3 key markets. One is the pro space or team performance. The second is media and technology. And third is around betting. So when you hear a lot of talks in this space, people tend to focus on team performance. However, in terms of the markets, most of the desire and most of the revenue comes from media technology and betting. So when we look through it in that lens, we have two buckets of content. And the first is precision. And what I mean by precision is just around graphics, officiating, and health. Okay. And so what I mean by graphics, and again, this is not a new thing. We actually had this over 20 years ago. Some of you may not have been born yet. So back in 1998, Sport Vision actually started having the first downline, and that still exists. You know, that's a must-have for any NFL broadcast or college football broadcast. The 2000 Olympics in Sydney, we had the world record line. Again, that's a must-have. Intel more recently have their TrueView system where they have 36 to 38 cameras, and they're able to reconstruct the view of a play. More recently, Second Spectrum have their augmented view, which is Court Vision. It's a really nice product there. And more recently, if you watch the NBA this year, there's a lot of really nice virtual insertions, and you probably don't even know they're virtual. So if you look at the NBA finals in the bubble, or more recently, those graphics are actually virtual. If you look at any TNT broadcast, they have the shot clock on the key. So when you're actually at the court, that you don't actually see that. You only see that in a broadcast. In terms of officiating, as I mentioned, you have Hawkeye in tennis and cricket, in goal line technology. And what's really interesting, if you have the upcoming World Cup this year, I think it's either Kyron Hago or Hawkeye, they're actually doing semi-automatic offside detection. And so instead of waiting 2 to 4 to 5 minutes for a decision, hopefully that'll be close to instantaneous. So I think that's a really great innovation, because it's great to get the right decisions, but it has to be very timely. And then Hawkeye are looking at doing this for basketball. There was an article in Sport Techie end of last year where they were doing some trials with the NBA, looking at improving the decisions, because a lot of time is taken coming up with the right decision with touches, last touches, and whatnot. So hopefully having these precision type of measurements can enable us to come up with not only the accurate decisions, but much, much quicker decisions. And then we have health. And so if anyone's worked in this space, the big foothold initially 20 years ago was with the sports scientists, and they use it for health monitoring. They want to know how far an athlete's run or how quick they're running. Now, if you look at what's been generated, they look at the fastest runner or who had the quickest speed over the season. Now, we have to be very careful because we have a lot of sports scientists and they don't know the error associated with tracking data, and they're looking at very short-term velocities. And then sometimes I've seen some analysis where they have a player running 100 kilometers per hour because they just don't know the basics of signal processing and the type of issues that we have. And if you look at the NBA, you can go to the NBA website and then you can find how quick or the distance is covered for a basketball player. But what's really exciting is not only do we have those applications, but there's a new vertical possibly emerging in sport, and this is the metaverse. So if you look at what Manchester City are looking at doing, they're trying to create this connected experience. And this is really the value of sport. Other than concerts, sport is something that is shared. You have to be there with other people. You can't really do it on demand. And I think with the metaverse, we're able to potentially unlock that. So anywhere around the world, you can have that same type of experience as someone in the ground. And so a lot of research has been looked into that. However, you need to get that right. You need to get the right registration, accurate registration to reconstruct that. And then that basically unlocks a lot of interactive applications. And that's something that we've been working on more in the scalable content. So in the precision content, we have this nice canvas here where we're able to unlock a value from a lot of these applications. Now, in terms of scalable content from trajectories, we can do a lot of interactive things. 5 years ago, I gave a talk at this workshop. I'm talking about all the great things we can do with interactive tracking data, or we can do visual search, we can do ghosting, we can do interactive formation analysis. But also there are other things that we can do in terms of creating descriptive content and predictive content. And really to unlock these type of applications. And so here are some screenshots of what we talk about with interactive AI. And we've done a lot of work the last decade in this space. People will probably be familiar with expected goals. We came up with expected goal value 10 years ago. We've just recently updated it. There's something called possession value, which can actually capture the value of every action a player takes in basketball and soccer. We have playing styles. I think Pascal talked about the semantics that they were generating with counter pressing and whatnot. So a lot of these things can be done, and it's pretty much a solved problem now. And then we can use that to generate predictive AI, whether that's recruitment or for betting. So really, to unlock these applications, though, we need to have tracking data for every game. And so this is an issue that we have in sports generally. We just don't have the coverage. And then there are other applications such as advertising and highlights. But the big issue is that to unlock the real value in sport, we need to have tracking data for every game. It doesn't matter that we just have it for one game, for one league. We need to have it for every game. So it's very much a coverage issue. And so even though we're tracking data, we can do the best analytics, we can have the best applications, we can't do it for every game. So it really diminishes the value. And so looking at broadcast tracking, where we do have the video, we can go back in time, we can go forward, we can do it for every league, male and female. Hopefully we can do it for every sport. And so that is really the next stage that we're looking at. We need to do this at scale. But because most of the applications, the key value applications are in media and betting, that has to be done live as well. So it doesn't matter if I can generate this after the game. To really unlock the value, this needs to be done live. And also there are limits to broadcast tracking. So I took this slide from Alyosha, I think his intro to computer vision at Berkeley. And then I think this screenshot was taken 20 years ago. Now, let's not be fooled. There's not enough information in the pixels that we see. So if we look at that, and because I played semi-professional soccer, I've been following it for 40 years, I can fill in the gaps. Even though the pixels tell me something else, I can really understand where that player is based on their relative position and whatnot. And so really computer vision still needs help. There are limits of what we can do with pixels. And so if we just look at a more recent video, Australia qualified for the World Cup last week. And if you just look at YouTube, the stream, again, you can see some of the players have distinctive features, but some of the players you just don't know. And it's very unfair to expect a computer vision system, first of all, to identify those players. So I think you can identify the teams and whether they're players or not, but it's very, very hard to know the appearance. And so if we just look at this player here and we zoom in, even though we have this video, it's very hard to get that appearance. And I don't know who that player is. And if we have trouble doing that, how do we expect a computer vision system to do so? Well, the solution really is leveraging other information. And as we progress, I'll talk about how we could potentially do that. Now, before I go into our solution for sport, let's look at what's happening outside of sport. And so really, it's a great time to be in computer vision, as we all know. So I remember going to this conference 12 years ago, it's rather small, but now, you know, it's 10 times bigger, and there's just been great progress. And I read Genius Makers, it gives a really nice story of what's happened over the last decade, and it really captures it nicely. I don't really need to tell this audience this. And a lot of the work is coming to industry because computer vision works now, right? But there's a bit of a transition. So there is a big gap going from research to industry. You're going from more science to more engineering, because I think the excellent talk this morning talked about it has to work 100% of the time, okay? Doesn't matter if you get your algorithm working for one clip. If it doesn't work for the whole game, you can't use it. And so I think Andrew Ning from Deep Learning.ai has come up with this term data-centric AI. You know, it's one thing optimizing for your train set and your test set, but really you need to optimize for your business goals, okay? And so to get that last mile, you really need to grind it out. And that's really the key thing for scalable applications. So if you think about where success stories are outside of sport, you know, obviously you can narrow the scope and you can do cancer detection for precision applications. If you look at Amazon Go, that system works really well. Where computer vision fails, they have other sensors, where they have pressure sensors or LiDAR, where they're able to actually pick that up. You have to register as you get into the store as well. If you look at robotics, that works really well if you can control the environment. And I'm not a big fan of Elon Musk, but I think he came up with a really good tweet last year where he talks about the issues that we have in autonomous vehicles, because it's been optimized for the human perception system, not necessarily a computer vision system. And so let's see how that applies to autonomous vehicles. So a lot of the people I worked with at Disney Research are now at Argo. And I think this gives us a lot of inspiration and learn a lot from what's happening in autonomous vehicles, because there's a lot of research, a lot of great work being done in this space. And where just normal computer vision systems don't work, they can use other sensors, such as IMU's GPS, and really they use maps. And this is something that we don't talk about. You know, there is other information sources that we need to really unlock the value here. And so in sport, really the question is, what is our maps? We need to have that framework where we can it's basically a language model. What's that important prior that we can narrow down the search space to actually solve the problems that we want to solve? And listening to a podcast by Raquel Ederson and what they're doing at Wabi, I think this is really nice. And this is a thing that we experience in sport. You need to have some inductive bias. You need to inject in that human intelligence, because otherwise you're just not going to have enough data, especially if you look at autonomous vehicles where you want to deal with edge cases. You want to deal with cars potentially running into pedestrians. How can we actually synthesize those examples? And so coming up with a digital twin, being able to generate this data and fill in those gaps is a way to do that. And that's something that we're doing within my group at StatsPerform. And tracking data enables us to do that, enabled us to synthesize these edge cases and come up with a good solution there. So really what we're looking at StatsPerform is scalable applications. So we don't have the ability to be in venue and throw more cameras. So for the semi-automatic offside detection, I believe they're going to 30 or 40 cameras to actually make that work. We don't have the ability to change that environment. However, we do have the ability to utilize other information. And that's what we really have to do for our broadcast tracking solution. And so as we kind of go back to sport, we have to look about the available information and what humans can do and what computers can do and what computer vision systems can't do. Now, if we look at a key metric that's been around for a long period of time, something called expected goal value. And expected goal value is telling us the likelihood of an average player scoring in a certain situation, given the context. Now, if we look at an example here from a corner, and we look at some of the features that are required. So over this corner from Southampton, it's headed back. If we pause it there, we have the players back to goal. He has a right foot volley. We have defenders all around that player. Then we have the goalkeeper out of position, but also the goalkeeper slouching to one side. Now, to get a computer vision system to do that is very difficult, right? To get the computer vision system to register that strike and get the level of the ball, know it's a right-footed volley, knowing that the goalkeeper is really off, and to do that live and to do that for every game is really, really difficult. However, at StatsPerform, we have a really good computer vision system, which are our humans. And we cover all these games, as I said, 100,000 games per year, and we're able to capture that data live. And some people will say, well, can't you use computer vision tracking to actually estimate that? Well, let's look at what computer vision data gives us currently. So we have our tracking system here. If we just play this, you know, we have center of mass. So we can infer where players are. It's really hard to know their direction, their body shape at a very granular level. It's hard to know whether they had a right foot volley or it's left foot volley. It's from a headed shot. However, we can get a human to do that. And at scale, and this is what we do really well at StatsPerform, it's not that expensive to do that. It's going to be far more expensive to get a very high precision computer vision system to do that. And so really, if you look at the value proposition in terms of shot information, we're really not going to get anything from computer vision data. We can get that from humans. But there's other parts of the game, especially in soccer, that we don't have, such as passes. So really, it's a fusion problem where we can fuse in together the human vision data plus the computer vision data, and we can come up with that solution. And so a couple of weeks ago, we've released our OptiVision product. And the OptiVision product is basically fusing together human data and computer vision data. Now, the issue with human generated data is even though we can pick it up at a very high level, the precision isn't great. So we can use the computer vision data to adjust to get the accurate onset and offset for these events. And so here we're just showing a play from Arsenal, and we're showing what we get with player tracking data and from our event data. And so what we're able to do is fuse it together. And we're able to augment the event stream with the tracking data and come up with a really nice combined data set. And so this is coming to market. We're releasing this for the start of the next season, and should help teams in a lot of ways there. Now, again, the value behind this is that it's enabling us to tell the full story. So instead of just finding out what happened at the end of a possession, we can use humans to do that. But the other things such as semantics, detecting things that humans can't do, such as off the ball runs or different playing styles, set play analysis and formations. We can use the computer vision system and the trajectories and merge that together into this sports perception layer where we can glean the metrics and semantics there. And from this product that we have, we can detect formations. For every pass, we can get the reward and difficulty of each pass. We can see how many times a player has an off the ball run. Again, really enables us to get the content and style of what's happening during a match. However, we do have an issue because that works really well when we do have an in-venue tracking solution. But what happens when we don't? So we have our broadcast tracking solution where we're able to do this. So we first unveiled this for basketball 3 years ago. Since then, we've collected over 10,000 games worth of college and international basketball. We're able to basically, from any broadcast, we're able to get the player positions. And really what unlocks this is the calibration. So we had a CVPR paper here in 2020, which I believe is a benchmark from what you have in the SoccerNet challenge. And really the key here is the segmentation and the line calibration module. Another thing that we do well with this system is the re-identification. And so we're able to use body pose to understand which way they're facing, and we can register the jerseys. But a key thing also is merging in the play-by-play data, the human-generated data. And we're able to do that to get a full picture or capture the full story. Now, in terms of accuracy, we're basically within 1 meter or 3 feet. Sometimes that varies, especially if you're at the far area of the court. And then sometimes when players are out of view, we're able to impute where they are. And this kind of gives a comparison of what we have for in-venue compared to what we have from broadcast tracking on the right. And then really how teams use this, we have a really nice partnership with the Orlando Magic, is they don't really use tracking data. So teams actually don't use tracking data because even though it's compressed, it's still not in a usable state. So we're able to project this into a semantic space, which is, again, a lower dimensional representation. So we do 2 things. First of all, we do event refinement, where we're able to get the precise frames of each of these events and the onset and offset. And then we're able to detect things in basketball, such as a pass, dribble, possession, post-up drive, isolation, ball screens, handoff, off-ball screens. We're able at each frame to measure who's defending who. And then from our broadcast tracking system, we're basically just as accurate as what you'd get from an in-venue tracking solution. So in our view, event detection is pretty much solved if you have a nice active learning interface and you have the right labels to learn from. And we've played around with different representations, just using handcrafted representations, work pretty well. We've used an end-to-end attention network that does pretty well. But again, just to inject in the inductive bias, you can just do feature engineering, and that does a very, very good job. And precision and recall is around 0.9 and 0.9. And also, we've been able to test the value of this data via a downstream prediction task. So we did a Sloan paper last year where, using our AutoStats data, we're able to predict the draft bin of each player. So we want to know the likelihood of a player making the NBA using our data, but also we want to know which draft bin they're in, which is what we're showing on the right. But also we can create these predictive reports where we're able to show the strengths and weaknesses. So we use Shapley values to actually use look at the attributes and see which ones are positively correlated within making them the NBA, which is in blue. And then in red is what we have the negative attributes. Using AutoStats data. And currently we're doing this for soccer as well, doing live. And so here's just a quick snapshot of the outputs that we're generating. So just to summarize, the way that I see it and the way that we see it at Stats Perform is really to really unlock the value of the data and computer vision data, it's not just a computer vision problem. It's a fusion problem. We need to fuse in what humans generate with computer vision, and then we can kind of link it at that higher level, and we can generate everything that we really need to. But the really nice thing is that we can make this full circle where all these things can be cyclic and connect back to each other. Now, in terms of open challenges, dealing with the edge cases, being able to calibrate a pitch or a basketball court for every game, there still needs work to be done there. Scene detection, a lot of the tasks that are wrapped up into the SoccerNet challenge. OCR, you may think is a solved problem, but it still doesn't work for every game. It's really crazy what happens during a broadcast. Some broadcasters will change a score bug. Sometimes a score bug will move up or down. Again, dealing with the edge cases. And again, it's very much an engineering problem. Player and ball detection using standard detectors works really well. Team affiliation, really extending to body pose as some open challenges for CV. Now, for humans, there is a lot of information. And again, I'm a big proponent of having this prior or this inductive bias where we can actually set the framework and use computer vision data to actually fill in the gaps. And then using the machine perception module, we can basically bring everything together, and we can have this kind of virtuous cycle where everything's helping each other. Now, in terms of open challenges, I just wanted to highlight one thing. I think what this team's doing with SoccerNet is great. In terms of action spotting, I think the talk this morning was great for automatic broadcast live, augmenting that. I think that you need that context. But in terms of using this as a product, we would probably never use action spotting as a deliverable because it has to work for every game, and getting humans to do that is relatively cheap. And so just kind of calling this out, I think it's great. It's a great way of evaluating progress, but as a viable product output, it's really not going to be used because a yellow card, goals, you need to get that right 100% of the time. So if that's 99%, you're not going to use it. And you really have to show where I do see this as tremendous value, detecting things that humans can't do, like off the ball runs, formations in basketball, off ball screens and ball screens, that works really well. But just for these standard things that we do as a company, it's got to be really good, much lower cost to actually, be effective. But so that's just some commentary, and hopefully that could be useful as you're looking ahead for the future ones. And I really like the way that you're approaching the tracking challenge too, because again, I've reviewed some papers. I've seen some papers where they're showing really good performance on 8-second tracks. Okay. Again, for us, to be useful in industry, you have to use the whole game. So if you miss a clip, it really isn't useful because often when you miss something, it's probably the most interesting part of the game. And so instead of just looking at clips, and I think the progress that you're making looking at those 12 whole games and looking at that evaluation is really pleasing because that's really it. So if you're missing some clips, that's often in sport what's the most interesting thing. And if clubs don't get that, again, they're not going to use that. So that's basically it. I appreciate the invite. Hopefully that's useful. It's a bit of a sneak peek of how we think about things in industry. And I think this is a great workshop. Again, appreciate the kind invitation, and I'd be happy to answer any questions if anyone has any. Okay, thank you.
I just was wondering, you mentioned the accuracy of the tracking data. How do you measure that? Do you use another sensor modality?
Yeah. So for how we evaluate the broadcast tracking, we had an in-venue solution. So we used our in-venue solution as our ground truth, which isn't perfect. But if you look at what FIFA are doing, they have some evaluations, like they call it the EPTS test, where they have a Vicon system and they actually compare to that. But to do it at scale, we're able to use the tracking data where we have in-venue, and then that's our benchmark. Yeah.
On a larger scale, when do you think that tracking specifically,
I think they're looking at solving that more with cameras. So 5 years ago, I thought it would be solved by now. However, it is very much the edge cases. So to get it working 100%, if you look at the occlusions happening at corners and free kicks, those are the edge cases. So I think you asked the question, someone asked the question this morning, when a player comes off and on, you have malingerers, they'll come off for injury and then they'll come back on. The game is evolving too. If you have the prize, like 3 substitutions, they're changing it to 5. Now you have head knocks. How do you deal with that? Also the use cases, are you using it for an automatic broadcast or are you using it for betting? If it is used for betting and a new market's emerged, how are you going to pay out on that? Maybe it's not done for team sports. Maybe it's easier for tennis or baseball or cricket. However, it has to be measured on a downstream application. It's not just solved. It can be solved for a specific use case. And so I think a lot of great work is happening in the Olympics too. If you're looking at, and I didn't put this in the slides, if you're looking at diving and those things where you can get that automatic feedback. I don't think they'll use it for judging at the event, but for training, I think that's of great value too. So, you're just replicating what those judges are doing. And again, it just depends on that downstream application task. Yeah.
Thanks for talking. So I had separated when trying to use broadcast videos, what happens typically is that you have strong zoom in, zoom out, and camera change. So during the broadcast, everything basically happens, right?
Yeah.
So I was wondering if you had evaluated also those scenarios.
Yeah. So that's part of the evaluation. So I think previously in SoccerNet you have scene change. So 50% of the time, the ball's out of play. So in soccer, you have 50 or 60% of the time is actual play. And so first of all, I think that's a reasonable evaluation. So how often is the game in play? And how often do you have actually broadcast tracking from that game view? Because they will do the zoom ins, they'll go for ads. If you look at other sports, they'll do picture in picture. So in terms of our internal evaluations, we do have those multiple dimensions in terms of game coverage. I think for broadcast, it's about 90% trackable. And sometimes it varies to 80%, depending on the director or producer, but that definitely factors into how we evaluate. Now, in terms of usable data, you could fill in the gaps where you have missing players, but something that we're looking at is if you have a 5-second break, where you don't see any of the players, how do you fill in those gaps, right? So, or if it's 10 seconds, and you do have the event stream, can you impute where the players would go, just knowing that, because the nice thing with our event stream is that we have that kind of constant stream of data. So just so you know, a pass or a long pass happened from point A to point B, over that 10 seconds that we don't have broadcast, how can we fill in the gap of those players across that 10 seconds? So that's another challenge, because you see some papers filling in the gaps of players out of stream, but I think another challenge is filling in the gaps where you have no video, because you do want to have that full picture of the game. Okay. Does that make sense?
Yeah.
Yeah. Yeah.
So obviously a lot of what you're doing is like macro. How much are you exploring using like keyboards to look at individual?
So we had a paper at Sloan 2017 looking at the shot location of the Golden State Warriors. Now, if you look at broadcast tracking, the accuracy is just not good enough for body pose. Okay. And even so, if you look at baseball, that's actually occurring. Now, in terms of accuracy in play, I don't think it's quite there. I think a lot of the analysis is still done in a lab situation. Hopefully, it's not just having more pixels, it's having frame rate as well. But for our work, it is kind of scale. So we haven't done that precise, but we have done some investigations, and from broadcast tracking, the accuracy isn't there, especially if it's far field. If you're off for a pixel or two, that's a lot of, that's quite a bit of noise there. Yeah. There's one more question. Yeah. Well, I think there's two things. I think in baseball, they've shown that they can do automatic officiating, just the strike zone. I think for soccer, the goal line technology is there. I think for the World Cup, they're doing semi-automatic offside detection because that's such a subtle thing. There are rules around that, like when the ball is played and the player's passive. So I think they'll get close to instantaneous there. I think for other things, I think they're exploring, touches and whatnot in basketball. However, I think referees are very good at what they do. And at the end of the day, sport is entertainment and there is some randomness and there is some, it's more exemplar based than rules. So I think when you're finding American football, they're going the letter of the law. They say, well, in this situation, what's a catch and what's not a catch? Sometimes it just looks like a catch. It's very hard to articulate via rules. So I think we're getting at a really good point where we will always need referees, to manage the game. And I think if they can get this semi-automatic approach working seamlessly, because then, and this is something I didn't talk about, you really need to get the right interface. How can you get the human to interact with computer vision data seamlessly? So I think that's an open challenge, but I think we're getting to that sweet spot where we can get humans to do what they do well and computers to do what they do well. So that's not really an answer there, but I think we're getting to that point. Yeah.
Thank you for your talk.
Okay. Thank you. Yeah.
If you just restart, then we'll take from there. My bad. Sorry about that.
So hi everyone, I'm Kanav and I'm here to discuss about our paper titled Ice Hockey Player Identification via Transformers and Weakly Supervised Learning. So basically the problem of interest here is to infer jersey number from tracklets. What are tracklets? So tracklets are basically output of a multi-object tracking algorithm. So basically you apply object tracking on a video and you get a lot of frames of a certain player, which is labeled as a tracklet, which can be of hundreds of frames, maybe even thousands. So basically the things which we have done is like in leagues such as NHL, we have this play-by-play data. And through this data, we know which players are present on the ice at a certain time. And we can help, and this kind of data can help in player identification. Moreover, as I just discussed, that these tracklets can be of thousands of frames. So basically, if you just have one label that, okay, this has jersey number 12, that is basically not enough, because if we sample from anywhere in this tracklet to train a player identification algorithm, it may be possible that the jersey number may not be present in this tracklet. So we need some kind of weak labels so that we can train these algorithms effectively. And we want to take advantage of the recent transformers, the attention mechanism that is famous nowadays. So basically, initially we have a tracklet. We need to somehow sample some frames so that we can train a CNN, because we can't input thousands of frames into a CNN. Then we have some features input into a transformer, which gives us the output probabilities. So without discussing the details, as I don't have time, I'll just show the results. So basically, as you can see, this is a tracklet, which the ground truth jersey number is 2, but it is heavily occluded by the number 12. So if I don't use the shift data, it gives me output as 12, the blue line, which is incorrect. But when I use the shift data, it helps us focus on only the players that are present on the ice rink, which helps in making the identification correct and improving the accuracy almost by 6%. Also, the weekly supervised training, in which we create weak labels for the presence of jersey numbers in tracklets, helps the training as well as convergence, which is basically the blue line, as compared to the red line where we don't use these weak labels. And ultimately, it performs better than the previous works on this kind of problem. And if you want more details about this work, please visit my poster. Thank you very much.
Okay, thanks. So localizing the ball in the 3D space has numerous applications, like enriching broadcasted content, assisting referees, or drive automated framing. The most widespread approach to get ball field localization consists in installing multiple cameras around the pitch and use triangulation to derive 3D coordinates. However, this type of multi-view setup is expensive. Moreover, 3D localization may be useful even though only one single viewpoint is available. In my work, I'm addressing ball 3D localization from a single calibrated image. When an image is captured, the ball projects onto a camera sensor, and with modern computer vision method, detecting ball position in the image space is quite easy, but the depth information is lost. However, by estimating ball diameter in the image space and combining the knowledge of the true ball diameter and calibration data, it's actually possible to retrieve the ball 3D localization. My work relies on two stages approach. The first stage is a detector that outputs the ball position in the image space, and the second stage uses a thumbnail around the position to predict the ball diameter. More precisely, the second stage is based on a simple VGG architecture trained to regress the ball diameter. And in addition to the regression output, the model also is trained to predict the presence of the ball in the image patch. Our study shows that this significantly improved the detection quality of the ball detector of the first stage. If you want to see the thorough investigation on which this research is built, please come to see my poster. And additionally, if you think you can improve on this very simple baseline, I invite you to compete on the Sport Ball 3D Localization Challenge that will be held in October this year, and there's a $1,000 prize to win. If you have questions, just come to see me. Thank you.
Are unlabeled data useless data? Well, if you think of a fully supervised approach, then yes. However, I will convince you that the answer is actually no. My name is Renaud Van de Gen. I'm a PhD student at the University of Liège, and with my co-author, Anthony Chopa, we proposed a new semi-supervised learning method. In particular, we will show you how to use both labeled and unlabeled data for object detection in soccer. Most of the labeled data you are using in your own projects will probably cost you both in time and money. But what if I told you that you do not need to label all of your available data? Indeed, pseudo label is all you need. Starting with a small amount of labeled data, we train a teacher model in a fully supervised way. Afterwards, we use the teacher to produce pseudo annotation on the unlabeled data, and each prediction is associated with a confidence score. Now that we have access to both labeled and pseudo-labeled data, we can use them to train a second model called the student. As a novelty, we use the confidence to either select or reject a pseudo-label, and we also use it to downweight the loss during training for unsure predictions. As a final step, We iterate the whole process multiple times to improve the performance. Let's now see a few results you can obtain starting with only a few thousand labeled images. In this sequence, you can see that the predictions are generally better for the student, especially for the staff class, which is extremely less represented in the label dataset compared to the other ones. If you're interested, please come see us at the poster session. We also have a complete video covering the topic on YouTube, and our code is available on GitHub. And remember, yes, unlabeled data are valuable data. Thank you.
Hello everyone, I'm Yutaro Honda from the University of Tokyo. Let me introduce our path prediction model in soccer scenes that combines players' video and trajectory for accurate prediction. Our goal is to create a model that can be used for analysis or entertainment for soccer scenes. We combine geometric and visual information to improve the prediction accuracy compared to those that only use player trajectories. There are three key factors for prediction: player's body motion, player's trajectory in the field, interaction between players. For the first factor, we crop the player's region from the video and encode it by 3D CNNs. For the second factor, we use an LSTM. For the third factor, we use a transformer and predict which player will receive the ball. We also developed an alignment method between the trajectory of the players and the coordinate of the wide-angle videos. It includes homography transformation, YOLO verified person detection, and refinement by using registration algorithms. We conducted an experiment to simply compare the prediction accuracy between our method and the baseline. As shown in red, the proposed model, which uses trajectory and video, predicted the path with considerably higher accuracy. We also considered possible applications that use our prediction model. The first is using probability change to detect key timing the player's decision changed. The second is using misprediction in order to search high-level path plays. Thank you for listening. For more details, please visit our poster. Thank you.
Hi, I'm Katja Ludwig, and I will present you the recognition of freely selected key points on human limbs. Video analysis is a popular technique used to improve athletes' performances in many sports disciplines. In individual sports, analysis are mainly bound to fixed, predefined key points that are costly annotated. With our method, we are able to detect arbitrary key points on the limbs of humans, which opens possibilities for new analysis. You can see some examples for predictions of our method in the images below. In order to solve that problem, we need to generate ground truth key points. At first, we randomly sample a point on the straight line between two fixed key points. Then we use the segmentation mask of the body part and an orthogonal line to sample the final ground truth key point. We represent these ground truth key points either as a vector based on the generation process or in normalized coordinates of a norm pose, which you can see here on the right. Our model is based on an architecture from token pose, which is a transformer architecture. The key point representations are converted to tokens and used as an additional input for the transformer. For our experiments, we need to introduce a new metric that measures the correctness of a thickness, which means the distance to the straight line between the two fixed points. Otherwise, a model predicting points on that straight line would achieve good results, but it does not learn the semantics of body part shapes. Experiments on the dense pose split of the COCO dataset and a triple and long jump dataset shows that our method works. Both representation types achieve good results in both datasets regarding typical metrics like OKS and PCK and the new thickness metric. If you're interested in learning more, visit our poster.
I will now have the video presentations. So just a sec. Oh, oops, my bad.
Welcome to this short presentation of team-sport players with frequencies determinations. Tracking team-sport players is useful to automatically measure individual performance. It is, however, a rare task since team-sport players move quickly, return with difficulty, oppose each other, take various poses, and wear the same jersey. To tackle this challenge, we designed a new framework that can track for players during the full games thanks to few user annotations. The first step is to detect the players. It is done with a faster access on the data. Then, the detection between the current and previous frames is managed to generate few seconds length tracklets. Now, our system needs to learn which tracklet corresponds to which identity. So, a user annotates the identity belonging to some of the tracklets thanks to a dedicated user database. The uniform sample image view from each tracklet has the uniform identification model. This model is then composed of a single image identification network on the transformer. Once our model has been trained, we can run the events of all the tracklets and associate each of them with a player identity. If there are many matching labels, the user can have more conditions on this type of connection. In the other case, we find the tracking results out. We evaluated our method on strictly 27 numbers on the full game. Our method can track players during the full game using the annotation of only 6 brackets per player if they are accessible using the identification. Thank you. I will introduce our work post-field registration for application. First of all, post-field registration is to assimilate transformation using field features with individual model image. This works in shape concept without transparent features. The recent features that standard by mid-level software to tackle the problem of traffic software features from UAE to computer appearance, we combine sources of visual dynamic capability to detect data info restricted to points over the computer image. And this software case workup with detailed diagrams of data consequence images. First, translated over the other, even include the image as double symmetry in order to connect to the traffic function map. Because available application with total ICT components and additional 100 data, and the general images solution using specific controller module. Finally, we leverage the solution namespace and learn solution theory and perform some application for each feedback to get final result. In summary, we estimate a robust number based on the three distributed ones we combine them as a case for please visit our webpage for more results. Thank you. In present, thank you and Irish reducing risk of severe injury such as concussion, is high priority for any contact sport. Concussion raises the risk of harmful output and is the most common injury in rugby. Therefore, it is important to keep athletes out of participation when there is any suspicion of concussion. Defining players with suspicion of concussion and keep them out of the game. In 2015, World Rugby introduced a massive concussion management protocol referred to as head injury assessment, HIA. However, HIA is conducted by training professionals, thus affordable only for elite members. In this work, taking advantage of recent progress in deep learning, we aim to develop a system that detects high-risk events automatically from rugby match data. In this work, we define high-risk tackle as tackle which led to HIA official match record, and develop a system to detect high-risk tackle from rugby match data. Our system consists of four modules, namely frame collection, tackle detection, hold estimation, and tackle risk classification. The system first takes 5 sequential frames from rugby match data and sequentially applies models and returns risk from tackle when tackle is detected in a given frame. For further details, please come to our poster. Thank you.
Hello. I am presenting our work, Watch and Act, Dual Interacting Agents for Automatic Generation of Possession Statistics in Soccer. We have proposed a computer vision-based method for automatic generation of ball possession statistics in soccer videos. 2 interacting DQN agents are proposed to detect valid passes. Then, possession statistics is generated using the valid pass counts of 2 teams. Existing valid pass detection methods follow 2 steps. In the first step, a ball passing event is detected. In the next step, the team information of the passing players are checked. Due to the 2-step nature, the existing approaches are complex, error-prone, and irrecoverable to errors. To avoid that, we have proposed a dual interacting agent-based model for single-step pass detection using a temporal window. Our model has an identification agent and a localization agent. The localization agent moves and rescales the temporal window and receives a positive reward if the window moves towards the ground truth window. The identification agent receives a positive reward if it correctly identifies a valid pass. Given a temporal window, the identification agent decides if the temporal window contains a pass. If there is no pass, the localization agent moves and or rescales the temporal window. This process continues till either a pass is detected or a maximum number of times. We have extended the dueling DQN architecture for communication between agents. The value of a state is shared as a message to the other agent for faster learning of key value. Experimental results. References. Thank you.
Hi everyone, and welcome to our spotlight talk. And the title of our post here is Interaction Classification with Interaction Detection in Multi-Person Sports Videos. We have two main motivations behind this study. Number one is understanding the interactions between the players is a key component of sport analysis. And number two is that often the sport broadcast videos are crowded with so many players, and some of them are involved in the main events presented in the scene, and the rest of them are not. So, bringing these two together, we propose a method that is able to recognize these interactions while implicitly identifying who are the key actors. Now, what is interesting is that our method does not require any explicit annotations of the key actors throughout the video. We apply this model to the penalty classifications from our software broadcast videos, and because our software broadcast videos offer so many challenges in terms of video understanding, such as complex scenes that are full of occlusions, self-occlusions, and there are camera viewpoints in terms of scale and angle, and a lot of camera motion. So, for more information about the study, and especially this work we discovered, please.
Okay, so that was the spotlight presentations. So now we have a extended poster session, which will happen outside of hall D and E below at the poster E87A to 206A. And this will last for the next an hour and a half. And after that, we'll have the last session of the day where we will hear the last keynote. We'll see the results of the SoccerNet camera calibration challenge, and we will present the best paper award. Yes, thank you. If you just stay on Zoom, then I will fix the videos for you.
Tracking teams for players is useful to automatically measure individual performance. It is, however, a hard task since teams for players who quickly enter deep in the field of view, augment each other, take various poses, and wear extend jerseys. To tackle this challenge,
Hello, and welcome to this short presentation. Hello, and welcome to this short presentation about efficiently tracking team sport players with few game-specific annotations. Tracking team sport players is useful to automatically measure individual performance. It is, however, a hard task since team sport players move quickly, enter and leave the field of view, occlude each other, take various poses, and wear the same jerseys. To tackle this challenge, we designed a new framework that can track team sport players during a full game thanks to few user annotations. The first step is to detect the players. It is done with a faster RCNN detector. Then, the detection between the current and previous frames are matched to generate few seconds length tracklets. Now, our system needs to learn which tracklet corresponds to which identity. So, a user annotates the identity belonging to some of the tracklets thanks to a dedicated user interface. We uniformly sample images from each tracklet as the input of our re-identification model. This model is mainly composed of a single image re-identification network and a transformer. Once our model has been trained, we can run the inference on all the tracklets and associate each of them with a player identity. If there are many matching errors, the user can add more annotations and restart the model training. In the other case, the final tracking results are obtained. We evaluated our method on 3 Rugby 7s 40 seconds samples on the full game. Our method can track players during a full game with the annotation of only 6 tracklets per player if they are observable with a minimal resolution. Thank you.
Hello everyone, my name is Yanrui Chu. We come from National Tsinghua University. I will introduce our work support field registration via key points available condition. First of all, support field registration is to estimate homography transformation using field features between 2D field model and image. While recent works have shown impressive results, some still have limitations. The recent key points-based method by Needle suffers from missing and misalignment problems due to repeated appearance. In order to tackle the problem of extracting sparse field features from field images with repeated appearance, we combine instance segmentation with dynamic filter learning to detect grid of uniformly distributed key points over the entire field image. And we introduced a new soccer dataset called TX Workup with detailed field markings on 3,812 time sequence field images. The first part, standard encoder-decoder, given an input field image, we adopt a symmetric encoder-decoder to extract the feature map. And the second part, key points available condition, we encode the ith key point as a 91-dimensional one-hot vector Ki. Then we generate the parameters of convolution filter using key point-specific controller module. Finally, we leverage 3 convolution layers based on learned convolution filters and perform soft aggregation for merging heat maps to get the final result. Comparing with the recent state-of-the-art methods, our predict homography estimation is better than others. In summary, we estimate a robust homography based on a grid of uniformly distributed key points and instance segmentation with dynamic filter learning, and we compile a new soccer dataset called TX Workup by annotating time sequence field frames. Please visit our webpage for more results. Thank you.
We present end-to-end high-risk tackle detection system for rugby. Reducing risk of severe injury, such as concussion, is a high priority for any contact sports. Concussion raises the risk of harmful after effect and is the most common injury in rugby. Therefore, it is important to keep athletes out of participation when there is any suspicion of concussion. To find players with suspicion of concussion and keep them out of the game, in 2015, World Rugby introduced the Matchday Concussion Management Protocol, referred to as Head Injury Assessment, HIA. However, HIA is conducted by a human professional, thus affordable only for elite league. In this work, taking advantage of recent progress in deep learning, we aim to develop a system that detects high-risk events automatically from rugby match videos. In this work, we define high-risk tackle as a tackle which led to HIA in official match record. and developed system to detect high-risk tackle from rugby match video. Our system consists of 4 models, namely frame selection model, tackle detection model, pose estimation model, and tackle risk classification model. The system first takes 5 sequential frames from rugby match video and sequentially applies models and return risk of tackle when tackle is detected in given frame. For further details, please come to our poster. Thank you.
Hello. I am presenting our work, Watch and Act, Dual Interacting Agents for Automatic Generation of Possession Statistics in Soccer. We have proposed a computer vision-based method for automatic generation of ball possession statistics in soccer videos. 2 interacting DQN agents are proposed to detect valid passes. Then, possession statistics is generated using the valid pass counts of 2 teams. Existing valid pass detection methods follow 2 steps. In the first step, a ball passing event is detected. In the next step, the team information of the passing players are checked. Due to the 2-step nature, the existing approaches are complex, error-prone, and irrecoverable to errors. To avoid that, we have proposed a dual interacting agent-based model for single-step pass detection using a temporal window. Our model has an identification agent and a localization agent. The localization agent moves and rescales the temporal window and receives a positive reward if the window moves towards a ground truth window. The identification agent receives a positive reward if it correctly identifies a valid pass. Given a temporal window, the identification agent decides if the temporal window contains a pass. If there is no pass, the localization agent moves and/or rescales the temporal window. This process continues till either a pass is detected or a maximum number of times. We have extended the dueling DQN architecture for communication between agents. The value of a state is shared as a message to the other agent for faster learning of Q value. Experimental results. References. Thank you.
Hello, my name is Atom Scott from the University of Tsukuba, Japan. Our research is titled Soccer Track, a data set and tracking algorithm for soccer with fisheye and drone video. We propose a new data set for soccer. The Soccer Track data set includes wide view video footage recorded with a fisheye camera in 8K and top view video footage recorded with a drone in 4K. We have fully annotated 50,000 frames with GNS location data and bounding boxes complete with IDs for tracking. This data set will be released publicly for use in academic research. Here are examples from the Soccer Track dataset. On the left, we have the wide view video example, and on the right is an example from the top view. Of course, the resolution has been heavily dropped for the purpose of presentation. In addition to the dataset, we also propose a new tracking algorithm. The Soccer Track algorithm is a baseline tracking algorithm that uses both visual and motion information. It works on both wide view and top view camera footage. It also utilizes prior information such as the number of subjects and the pitch area. The code for this algorithm will also be publicly available. Please see our paper and poster for more information. The dataset and related project code is available on GitHub via the link displayed, or you can just Google Soccer Track and find us there. Thanks for listening.
Hi everyone, and welcome to our Spotlight Talk. And the title of our poster is Interaction Classification with Key Action Detection in Multi-Person Sports Videos. We have 2 main motivations behind this study. Number 1 is understanding the interaction between the players is a key component of the sport analysis. And number 2 is that often the sport broadcast videos are crowded with so many players. Some of them are involved in the main events presented in the scene, and the rest of them are not. So bringing these two together, we propose a method that is able to recognize these interactions while implicitly identifying who are the key actors. And what is interesting is that our method does not require any explicit annotations of the key actors throughout the video. We apply this model to the penalty classifications from ice hockey broadcast videos, because the ice hockey broadcast videos offer so many challenges in terms of video understanding, such as complex scenes that are full of occlusions, self-occlusions, and there are varied camera viewpoints in terms of a scale and angle, and a lot of camera motion. So for more information about our study and a discussion, please feel free to stop by our poster. See you soon.
Beginning the session again, and we are at the last part of the day. So we'll have the last keynote given by Silvio Giancola just in a minute. Then we'll have the results of the SoccerNet camera calibration competition, and in the end we will conclude the workshop and also give out the best paper award sponsored by EVS equipment, broadcast equipment. So let me just share the screen and then I'll give you the word to you, Silvio. And I'm just going to say that you're a research scientist at King Abdullah's University of Science and Technology. Right. The floor is yours.
All right. Thank you for this introduction. So hi, everyone. My name is Silvio Giancola. I'm a research scientist from King Abdullah University. Oh, wait, just let me check this. Okay. So today I will present you the progress in our project SoccerNet, large-scale datasets and benchmark for soccer video understanding. Clicker. Okay. So a few words on myself. I'm a research scientist at the King Abdullah University of Science and Technology, also known under the acronym KAUST. KAUST is a very young university in Saudi Arabia, in the border of the Red Sea, where we enjoy some very nice facilities, both in terms of research, foundings, and support, which actually led us to a very nice ranking over the last 5 years in terms of publications. We are actually in the top 10 of the world in the famous CS ranking website for visual computing, which includes like computer vision, computer graphics, and visualization. So I'm part of a laboratory called Image and Video Understanding Laboratory under the supervision of Professor Bernard Hanem, affiliated with the Visual Computing Center and the Artificial Intelligence Initiative. In this lab, we work extensively in video understanding and created the SoccerNet challenge, the SoccerNet datasets in 2018. But SoccerNet is not only about KAUST, it's mostly a great collaboration with many actors all across the world, both from academic and industrial backgrounds, with, of course, deep interest in soccer video understanding. And in particular, I would like to acknowledge like Anthony Chiopa and Adrien de Liège, without whom SoccerNet wouldn't be what it is today. So you might ask, why soccer video understanding, and what are the application of such tasks? So in video understanding in soccer, we focused on action localization, answering, for instance, at what time does a goal or substitution occurs. We also focus on automatic. We also can apply our research on automatic video summarization, finding, for instance, salient moments of a game. Video retrieval, finding the game where Messi scored from a free kick, for instance. Or we can also do extended statistics. How many goals Messi scored last season, for instance. So prior to SoccerNet, the research community was lacking publicly available large-scale data sets in those tasks. So what previous people were basically doing is that they were evaluating their own research on private data and not sharing that. So it was basically impossible to compare the findings of multiple universities nor benchmark those methods in a fair way. That's why we try to emphasize with SoccerNet. So in this presentation, I will review with you our work in SoccerNet with our attempts in bringing scientific rigorousness in this soccer video understanding field. So I will present you our large-scale soccer video dataset consisting of more than 500 videos. Then I will present you the different tasks and annotations that I split between the temporal tasks and annotations. You will see action spotting, replay grounding, and broadcast understanding. Then I'm going to introduce like the spatial tasks that are more pitch localization, camera calibration, and player identification. And more recently, we gather spatial temporal annotations for the task of multiple object tracking in continuous soccer videos. And finally, I will touch base on our benchmarking challenges that we have proposed over the last 2 years in collaboration with ActivityNet and CVsports. So first, allow me to present SoccerNet, a large-scale datasets for soccer video understanding. This work was published in 2018 during the 4th edition of CVsports, where I was giving a very similar talk to very similar people. So I kind of feel like we're back to normal in-person conferences. And this paper was entitled SoccerNet, Scalable Datasets for Action Spotting in Soccer Video. So this work was both a dataset and a first attempt to introduce meaningful tasks for soccer video understanding, both from the research part at least. I gathered like 500 complete games from the 6 main European leagues, including La Liga, Liga, Bundesliga, Serie A, Premier Leagues, and the famous Champions League. So we gathered a total of 764 hours of videos. That's worth a full month if you want to watch them all, for 3 seasons ranging from 2014 to 2017, all of them with at least 2 times 45 minutes, plus eventually the additional times for all those games. So with this data set, we introduced a novel task as well that we branded action spotting, which is a temporal localization task. You might be aware of TAL, temporal activity localization, but here the main actions are anchored with a single timestamp because the start and the end of a specific actions might be blurry. In 2018, we focused only on a few events even classes like cards, substitutions, and goal defined following the rules of soccer. Like a goal, for instance, is the instance, the frame when the ball crosses the goal line. So how does SoccerNet compare with the other video dataset back in the time of 2018? Well, it was the largest data set back in the days, which was ActivityNet, and which was focusing on generic videos instead of fully sports or soccer videos. So SoccerNet was the largest data set in terms of duration, with 764 hours of worth of videos. And the annotation were extremely sparse, with only 8.7 events every hour. So only a few hours. So only a few annotations. So looking for those class of actions is like looking for a needle in a haystack. But most importantly, this work was an opportunity for us to start a journey from a fresh new perspective with uniform data, easily accessible to the whole community. We provide high quality videos at 720p and 25 frames per second, low quality videos at 224p and 25 frames per second, and a set of generic frame features at only 2 frames per second. Those are typical frame encoding that provides a compact representation of the video in time. Now you might ask, why 224? Do we need like the features? Well, first, frame features are the input for many video tasks for temporal activity localization. It's because like it's very difficult to store full videos on the GPU. Second, the 224 format is the input of most frame and video encoders. Usually ResNet, for instance, only encode at 224 by 224. So there's no necessary need for 720p videos. So that's why we also provided the 224p videos, which weighs roughly 20 times lighter than the 720p. And third, that's a very good features that we have, is that those features are not visual data anymore. So it technically does not necessarily have copyrights. We can easily distribute that to the community. But we don't only like provide the uniform data, we also package them for easy distribution and integration in larger projects. We build a pip package with functions to download our data, with specific functions to download videos, features, annotations, and we have development kit for each of the tasks I'm going to present in the next slide. So then in seconds, I'm going to talk about our scaling up SoccerNet with temporal annotations on broadcast soccer videos. So it's more focusing on temporal tasks and annotations that comes with those SoccerNet videos. The work was published in CVsports 2021. We actually won also a Best Paper Awards. Thank you very much for that. And we're very well accepted by the reviewers as well. It was entitled SoccerNet V2, a datasets and benchmark for holistic understanding for broadcast soccer videos. The scope of this work is to provide data and tasks aiming at understanding soccer game at a very high level, mostly temporal. First, we scaled up the temporal labels with 300,000 manual annotations and includes 50 novel challenging games that we use in a challenge. So we basically segregated those annotations such that people can compete without overfitting on those data. Then we proposed 3 main tasks that focus on temporal aspects, which are the action spotting, the camera shot understanding, and the replay grounding. Those 300,000 annotations extend the previous SoccerNet annotations and provide additional information on the camera views. In particular, we extended the annotation for the soccer actions from 3 to 17 classes, providing more than 100,000 annotations that include the action class, the team, and whether that activity is shown or not. What does that mean, shown or not, is because spotting unshown actions, like for instance, when the ball goes out, but you don't see it on the main camera, it's more difficult, but you can still infer that information if there is like a ball throw in the field again. So additional to the actions timestamp, we also labeled the camera shot with 13 classes of cameras, including the main cameras, close-up cameras, and some others. We labeled the type of camera, the type of transition with the previous camera, whether it is like a smooth or there is a logo appearing, for instance, and whether the shot was live or replayed from a previous action, for instance. Overall, we investigate 3 main tasks for a complete temporal understanding, which includes the action spotting that I already introduced before, and we'll introduce also a bit better later on, which is basically localizing when and which soccer action occurs. Camera shot understanding, which is basically classifying which camera is currently shown and identifying the temporal boundaries of those different scene cuts. And replay grounding, basically localizing when an action shown in a replay actually occurred in the live broadcast. So those were basically our attempt to fully understand the temporal aspects of video soccer broadcast. Third, let's talk about spatial tasks and annotations that comes with the SoccerNet videos, in particular for spatial annotation for low-level understanding. That work was recently accepted at the Nature Scientific Data journal, and it is entitled SoccerNet v3, Scaling Up SoccerNet with Multi-View Spatial Localization and Re-identification. So in this new iteration of SoccerNet, we wanted to analyze soccer broadcast at a lower level, understanding the cameras, the field, and the players themselves. For that, we leveraged the annotation of the replayed action from SoccerNet v2, where the same scene, the same action is shown from different cameras. So we annotated the exact timestamp when the action occurred in the replayed clip to ensure that both frames are actually synchronized. And then from that, we provided annotations for the lines and the goals in the pitch. And then we provided bounding boxes of players, referees, staff, and ball. And we have multi-view matching for the same players in the field from multiple views. So overall, we gathered 1.3 million annotations on top of the previous 300,000 annotations that come from SoccerNet v2. This annotation includes, like for instance, the timestamp for the frame of the replayed actions, the points defining the lines of the soccer field, the bounding boxes for the players, the referee, the ball, as well as the player correspondences with jersey number as well, when those were visible. So those annotations enable 3 main tasks that were presented yesterday and later, which are pitch localization, which is basically the scope is to recover the position of the field in from a single view. Camera calibration, aiming at recovering intrinsic and extrinsic parameters of that camera. And player re-identification, basically aiming at retrieving the same players from different perspectives. So last, let's introduce actually spatio-temporal tasks and annotations that comes with, against the SoccerNet videos. That work was actually presented earlier by my colleague, Anthony Chopa. And it's entitled SoccerNet Tracking, Multiple Object Tracking Datasets and Benchmark in Soccer Videos. So SoccerNet Tracking is actually a whole new data set in terms of new videos and new annotations that does not come from the same 500 games that were annotated temporally and spatially. And it enables multiple object tracking in soccer videos for all the interesting classes of people, like a player, the referee, the ball, and so on. And with a challenging setup for a long-term re-identification and tracking of the players. So I don't want to repeat too much, but basically the dataset is composed of 12 complete games from the 2019 Swiss Super League, shot at 1000 ATP at 25 or 30 frames per second, using only the main camera. That's the main characteristics of those videos. For 11 of those games, we selected 200 actions of interest from the spotting task, the 17 classes that we defined from the spotting, and from which we extracted 30-second clip corresponding to challenging sequences for tracking. And for the last game, we annotated the complete halftime for a long-term tracking, where we provide a unique tracklet for all the players for 45 minutes non-stop. So extremely challenging setup. As mentioned, we provide tracklet of players, referees, and ball, meeting the SoccerNet standards in terms of data distributions and benchmarking that I presented before. Our annotation are aligned with the common dataset in tracking, which is extremely important for us for maximum compatibility with the existing algorithms already developed by our MOT community. And on top of that, in that specific case, we also included the jersey numbers when those are visible. Here's some example of the annotations for a shot on target. So I think maybe player number 7 will actually shot, or maybe it's another one. I don't know exactly. So each 30-second sequences are composed of 900 frames that are all annotated with jersey numbers when visible. And we believe that those annotations are extremely useful for soccer understanding, could support many research in the future, including re-identification as well as spatial temporal action localization, and or jersey identification simply from tracklet, like was presented in a previous paper in that conference. SoccerNet tracking is not only the largest tracking dataset in soccer, it's also actually the largest dataset in multiple object tracking, with more than 3.6 million bounding boxes for all those different objects to track, and people as well, and more than 5,000 different tracklets. To wrap up on data and annotations, I would like to emphasize how SoccerNet become really a go-to data set and benchmark for to benchmark basically soccer video understanding. So we provide data and annotations for most tasks in soccer video understanding, with temporal tasks such as action spotting, replay grounding, and camera shot segmentation with SoccerNet V2 and V1. We provide also like some spatial tasks with player re-identification, pitch localization, camera calibration, and more recently, spatial temporal type of tasks with multiple object tracking. And the amount of annotations is more than enough to investigate a lot of tasks at any scale, with a total of like more than 5 million annotation. So far, our data set for those tasks that originate from the numerous iteration of SoccerNet, including action spotting from SoccerNet V1, replay grounding that was including from SoccerNet V2, SoccerNet tracking that was the paper recently presented, and SoccerNet V3 that enabled pitch localization, camera calibration, and player re-ID. But since SoccerNet V2, we also kept the annotation for 50 games segregated. Those annotations are kept secret, so no one can train algorithms on them. So we have organizing for the last 2 years challenges on those videos, so participants can compete on our task and win money prize, but mostly maybe like some celebrity a little bit, and advertise their methods and research group as well. So last year we organized our first challenge around action spotting and replay grounding. And it was sponsored actually by Second Spectrum. And this year we have scaled up our challenge with 6 different tasks, split in 4 main topics, with a $1,000 prize for each of them, provided by our sponsor Sportradar, EVS, and Baidu Research. So let's investigate a little bit more about those different tasks and how did we define them. So action spotting is a task of localizing when and which soccer action occur. Replay grounding is very similar. It's identifying where the localization occurs for a given replay camera shot. So for both those tasks, we gather the 550 broadcast games. 500 are annotated for training purposes, while the annotation for the remaining 550 are kept secret to preserve generalization of those tasks. And the task consists in localizing, like for action spotting, 17 different events, including penalty, kickoff, goal, substitution, offside, shot on target, and so on and so forth. For each of those tasks, we provide development kits, including how to download data and how to train a baseline out of that. So anyone can actually train those algorithms and test them with some pre-trained models that we have provided. So it's really easy for our participant to compete in our challenge. And the result of this year actually are displayed here for the action spotting. It was really a fierce competition with several participations in the last months of this challenge. But a bit of insight of what do you think is actually challenging in this action spotting. What we noticed is that, first of all, action spotting is split in 2 stages. First, we have video, or at least 2 parts of the network. First, we have a video encoder, and then we have like a specific head that focus more on spotting or on grounding. But from the video encoders, what we noticed in that challenge is that people are running away from CNN, whose 3D CNN was very famous in like 2018, 2019, 3D CNN, ICNN, I3NN, R2+1D, and so on and so forth. People are trying to move to transformers with VIT and stuff like this. We also realized that context aggregation and self-attention mechanism play a very important role in time as well. People were also trying spatiotemporal features instead of just focusing on purely spatial features. And they were using also extra audio feature to complement the visual features. And for the spotting and the grounding heads, it's mostly adapted from temporal activity localization methods. Some interesting group was working on like dense detection anchors, grouping some specific actions that looks very similar to each other's. And one of the team actually ended up training end-to-end, both the encoders and the heads at lower temporal and spatial resolution, which is extremely challenging. It's one of the biggest challenges in video understanding nowadays. That's for one task. Another task that we introduced that I introduced with the SoccerNet v3 was actually the task of field localization, where the task is to detect the extremity of every soccer pitch element. We provide more than 20,000 images, and annotation is basically 2 points per line. And we have different type of objects, which actually kind of class of semantics, which is, for instance, like the big rectangle and so on and so forth, like the different lines. Similarly, we have introduced camera calibration. The definition of the camera calibration is to estimate the intrinsic and extrinsic parameters of the camera. And it also composed of more than 20,000 images. And the annotation that is provided for that is actually the soccer field lines that you can use with like a reprojection error in that case. Again, for camera calibration and field localization, we provide an extensive dev kits and way to download those data. Feel free to visit those websites to check how to train camera calibration network. I won't share the results yet because we have a full session on that in the next half an hour. So the player re-identification is defined as identifying each player across the different cameras views. For that, we basically have built thumbnails. We have more than 300 thumbnails that are different classes of objects, like the player, from which team they belong, the goalkeeper, the main referee, the side referee, the staff, and so on and so forth. And basically, it's annotated with assignments like with identity, basically unique identity between multiple views. So again, we provide a way to download with our BIP package all the data, all the development kit that you need to start with that task. And feel free to have a look at that website to play around with like some baseline that we provide for re-identification. Again, the leaderboard was quite inspiring for this challenge. We have a lot of participants. It was fierce, and Inspur, the team from Inspur, actually won yesterday, and we announced that yesterday. So some insights. Most of them were using the FAST3ID framework for player re-identification. The best participant was using Trans3ID SSL baseline with a VIT backbone pre-trained on LU person. And what we figure out is that pre-processing is extremely important. Removing IDs, for instance, with too few samples, and unsupervised domain adaptations is also very important for in the challenge set. And data augmentation can boost those performances, whether it is horizontal flip, random cropping, and so on and so forth. Last but not least is a task of player tracking, where the task is basically to recover the trajectories of multiple objects in time. We actually provide 100 clips of 30 seconds. That's just for the training set. And all player tracklets are annotated with the bounding box, and those were provided, the ground truth bounding box. And the scope was just to retrieve the trajectory. So purely an assignment task for the MOT experts. We have 5 classes of objects that you need to track, which are players, goalkeeper, referee, staff, and ball, which makes a bit more, which makes like fine tuning kind of necessary, because most of the MOT tasks focus only on people. And of course, like fine tuning on soccer players is extremely important. Again, we have full development kit to download those data, and we have implemented some baselines for you to kickstart on that challenge. The winner of that challenge were the Calisteo team, and it was like also a fierce competitions over the last months in particular. So some insight that we will figure out of is player tracking something easy to do in soccer context? Well, it was mostly about assigning detection results in our task. And basically, it was basically focusing on having strong re-ID modules. Some of the participants were trying to forecasting the player motions, like using Kalman filters and trying to figure out a way to embed motion priors on the object to track. And others were using a very soccer-centric strong priors, like modeling, for instance, the camera motion and understanding player position in the field. For instance, if you disappear from one side of the field, you won't reappear from the other side of the field. So just to summarize a little bit of our journey so far that we have introduced. In 2018, I introduced SoccerNet. SoccerNet is born with 500 games and one task that was action spotting. In 2021, we are including new temporal annotations for actions, replay, and camera. And we enabled 2 challenges that were also during this CVPR last year for action spotting and replay grounding. And in this year, we have new videos of the main camera for only 12 games that enables MOT, and new spatial annotation for field lines and players, a new task for field localization, camera calibration, and re-ID challenges, which makes a total of 6 different challenges. But the main questions that's remaining is what next? So first of all, the take-home message is that soccer video understanding is far from being solved. There is like still some challenges. You heard like this morning that they're aiming at 100%. Maybe action spotting is a bit too challenging for the time being, but we hope that in the future, those gaps will close significantly. So what's next as well is like, we focused a lot on broadcast understanding. We actually sponsor working on broadcast and understanding those broadcasts. So what if we can we support soccer teams as well with video understanding? Can we understand like the player positions, for instance, and try to support teams, professional teams, in building like analyzing like videos of other teams, for instance? How can we also improve refereeing? Can we have an automated VAR or something more advanced for that, like understanding which foul is that, for instance? Does it deserve a yellow card or a red card, for instance? Can we support also maybe medical staff, like trying to understand if someone gets injured, or try to include a little bit more of physiotherapy in that and stuff like this? Also, the second point of what's next is maybe we need also a final level of granularity. That comes with different aspects, not just like bounding boxes, but maybe having like a skeleton tracking, for instance, could be something extremely interesting for the future. We can also have like generic classes as well, like a different taxonomy of a hierarchical taxonomy of those different actions. Like, okay, you recognize it's a foul, but what type of foul is that, for instance? And in a refinement also, we can actually investigate captioning. Can we actually create a full text out of a specific actions that can be useful for automatic commentaries, for instance? And finally, our algorithm actually more than just for soccer. Can we transfer the learning learned from SoccerNet, for instance, to other sports, basketball, for instance? I know like many of the people here actually working with video of basketball. Can we learn, for instance, a re-identification network or module that would work as well in basketball? The task looks very, very similar. So a little bit more about like the impact that we had over the years, that I think is maybe also like one of the reasons why we still continue working on SoccerNet. We have a lot of interest, a lot of visits, a lot of view on YouTube. To be honest, I never thought that to grow SoccerNet to that level, because it's very like a niche applications. CVPR is more about like something very generic, but apparently the fact that we are all here gathered here is that that's a meaningful application to have. So we organized so far 6 challenging tasks. We have a community on Discord of more than 300 researchers. And just in our challenge this year, we had more than 600 submissions, which is really more than what we actually expected. So we hope that SoccerNet will continue in the future to challenge the computer vision community in numerous tasks, and that will help the research community to progress in soccer video understanding. And last but not least, but it's a bit like some insight, like how to make impact. What is the secret formula that we figure out maybe to make such an impact with that? So first of all, sharing data is extremely important. Why is that? Because it enforces reproducibility. like code. We often talk about reproducible code, but if the data are not available, you cannot reproduce the same performance on a private set of data. Organizing challenges is extremely important because it attracts talents. We had a lot of submissions because we organized challenges. People working on MOT were challenged to get the best performance and solve the task of tracking in soccer context. And the key here is not necessarily to try to start from scratch and not being an expert on MOT and expect to be like the best performances. Is actually, let's try to attract those experts in X. X can be MOT, re-ID, field camera calibration, action spotting, video understanding, to soccer understanding. And by uniforming those data sets and following the standards that is used in their field, that's how you ease the burden of those experts to join our community. So just to conclude, that's like the paper of the SoccerNet series that started in 2018 and proceeded like up to today, actually. And will hopefully continue in the future. And again, it's a team effort. I initiated SoccerNet in 2018, but now as you can see, the team has grown a lot and there's a lot of actors that help me provide all those different tasks for all those different research communities. And with that, I finish my talk. Thank you for your attention, and you have some space for questions as well.
A question about rights and data collection. Like, how did you? What were the challenges? I mean, you talked about use the data sets and work, but like getting it, collecting it, historical.
Yeah.
I'm sure.
So we started, yeah. So we started in 2018, actually, with 2017, actually, with a collaboration with Qatar Foundation that had access to all those videos. But it's quite impossible to share those videos, and usually copyright holders are very reticent in sharing those data. So our solution for that is quite simple. We were still able to collaborate with people as soon as those data do not share. So we instead like a kind of an NDA. So if you want to access those videos, you just sign this NDA that we approved, and basically says that you are the holder of those data, and you cannot use that for other things than just research. So because copyright is meaningful only if you make money out of it. This is just benefiting the companies, the research, not the companies. That's one way of proceeding. Another way of proceeding is that the copyrights are actually from the videos themselves, but all of those video understanding tasks actually use features. If you are familiar with ActivityNet or Ego4D or all those video data sets, they don't share the whole videos because they are heavy. And anyway, they're going to take those videos, extract frame features, and deal with those frame features. So most of the tasks can actually be solved with those deep frame features that do not hold any copyright anymore because those are not visual data anymore. So those were like maybe the way for us to share this data with the research community, which is a bit more complex, of course, to share with like for industry that might have commercial application out of that.
Where are you going next?
That's a good point. So as I mentioned, like most of our applications are very broadcast focused. So trying to support broadcast by having like tracking of the different actors, understanding like maybe how to generate highlights and kind of things. But actually what I see is that there is like a 2D table. We have multiple computer vision tasks that can be used for many applications. Those computer vision tasks are basically the 6 challenges I just presented that can be used for broadcast. But how about supporting the teams, like the professional teams, by understanding the strategy of someone? How can we support medical staff as well and trying to, like for physiotherapy, for instance, FIFA got interest in mapping the impact of the ball with the head of the players to understand if there will be like some concussions or like some strengths or something that will maybe impact the players. So we would like not to only focus on supporting broadcast, but supporting any type of actors that can use those videos of soccer. And of course, if you came up with like a research problem that you think that is extremely challenging, that could be the next task as well. So maybe captioning, having like captioning could be like extremely interesting for us because we actually have the data for captioning since 2018. It was included in the first version of the SoccerNet that I have not presented here, but we can solve for captioning. You can generate commentaries automatically, for instance. Maybe we can have something more fine-grained, like what if I cast like a task of retrieval of like, I want to search for all the videos that contains Messi that score a goal with the head. That's something that is not solved yet. Maybe like some broadcasters as well are very interested in proposing like some highlight of specific players, doing some specific actions or the best top 10 goals of the season. And they need to look for all those contents. And that is maybe extremely time consuming. And if it's not properly labeled, it's very hard to watch all those videos, basically. So that's maybe the answer that you were looking for. Thank you. Sure. Oh, of course, you never like label from scratch, or at least you avoid that as much as possible. If you know that object detection is, or player detection is almost solved, not 100% like the industry would like to, but if you can reach 90%, you don't want to annotate those 90% that are properly labeled. You just want to correct the mistakes of those algorithms. So that's one of the approach, more like active learning. So the first version, we annotated that by hand. We parsed some information from online website as well. So for instance, the spotting is like a timestamp at the second accuracy. You can find like those annotation at the minute accuracy online by just parsing some websites. So it's just a matter of like fine tuning those like having a more fine-grained type of annotations. Then we also leverage actually like some community workforce as well, some students or some people that are willing to collaborate with us. And in the last task of multiple object tracking, we relied on external companies as well that were supporting us by providing tools to automate that annotation process, or at least optimize that annotation process. But yes, it's extremely time consuming. And hopefully what I'm looking for is that in the next version of like SoccerNet, we rely less on data or less on annotated data, having something like more towards semi-supervised learning or full self-supervised learning or fully unsupervised learning, maybe. Yeah, sure. It, it depends. It depends on the task. For action spotting, for instance, you don't need like high resolution in spatial, not even in temporal, actually. Like 2 frames per second are more than enough to spot when a goal occurs. Now, for the task of tracking, re-ID, and everything, of course, the higher the quality, the easier it is. But now, nowadays, like for instance, for those tasks, people are using 720p videos or 1080p videos. I don't know if having a higher resolution would help. Maybe for the re-ID for sure, because you're already cropping these things. But for instance, if we have a task of player or like field localization, having a higher resolution map would actually means also more compute power. So it's not necessarily like something that is beneficial, actually. Of course, for skeleton, we will need like a high quality videos, of course. 1080 is my minimum. The more the better. But I'm pretty sure like we can leverage also some new techniques in super resolutions that would help to solve for those tasks at even lower resolution. Yeah. Thank you. Thank you.
So before I give the word to Anthony and Florian for the SoccerNet competition challenge, I just want to remind all the authors of the papers to vote for the best paper award. We will close that within the next 15 minutes, so we can be ready for the end of the session. But yeah, otherwise, we just need to stop computer so that the SoccerNet challenge results can be presented. So let me just quickly. Okay, and then. Let's get this. Jeg har lige gjort dig til host, fordi jeg er usikker på, når du klipper ud, og den så bare hoppet af. Så det er bare lige for at være helt sikker. Share screen, you can say share sound as well. Then replace the sound from the computer directly on. Share sound. You should do that when it shares directly for the Zoom. That's perfect.
Okay. Also, you should choose the headphones output. I think you have the Epson projector output.
On vérifie encore. C'est bon ça?
Non, ça c'est Epson justement.
Ah, ok.
Et alors, il a dit de changer en mettant headphone.
Oui, c'est tactile.
Ah oui, pardon.
Headphones. Ok. Donc. Ouh, ça a l'air de bien marcher.
C'est bien.
Ça, c'est bon. Et attends, il faut encore share sur.
Ah oui.
Il est presque. Share sound. Hop. Share. On est bon. Can somebody confirm on the Zoom meeting that the sound is okay?
Is it okay? Perfect. All right. So hi guys again. So before we close this very cool workshop that we've been together today, we will present now the SoccerNet calibration challenge. So as you've heard from Silvio just before, we've had this camera calibration challenge on which people were actually competing this year between March and June, right? And so we're going to present the results. But before that, I will just go through a bit of the, so we will have a very quick overview of the SoccerNet 2022 challenges. Then we'll talk just a bit about the calibration dataset itself, which has not been presented in details yet. Then we'll move on to the goal of the challenges and the different tasks, which were pitch localization and camera calibration, for which we will give the floor to the winners for a very short presentation of the methods that they used to achieve their great results. And finally, we will conclude our SoccerNet challenges for good this year, but we'll be back next year. All right. So as a review of the task, as Silvio said, for the ones that weren't there just before, we had 6 tasks this year: action spotting, replay grounding, player tracking, pitch localization, camera calibration, and player re-identification. So now we're going to focus on the 2 bottom left tasks in this talk. So just a few statistics before going into, just to show you a bit the impact of SoccerNet worldwide. As you can see, like we've had a lot of impact all around the world, especially in the US, Europe, and China and Japan, but also some people that are starting to join recently from Latin America, so South America, and as well as Africa and India, which is very cool to see that people from around the world are gathering to compete on our challenges. So Yeah, so these are mainly the statistics to show you that the United States, Japan, China, and basically Europe are the most prominent actors in our challenges. We have also a community on Discord now, grouping 300 members. So feel free to join us on this community that's basically talking about the SoccerNet dataset and challenges. If you're interested, we're very eager to welcome you, of course. So this year in total, we had 637 submissions and around 10,000 views related to our SoccerNet dataset on our YouTube channel that you can find right there, where we talk about much more different works related to artificial intelligence and video understanding. All right, so the dataset itself, so we extracted the frames of camera calibration from the 500 soccer games that were present in the SoccerNet dataset. And this comes from 6 main European leagues. And we extracted 21,000 frames, as you can see, during key actions and replays. So for instance, during corners, goals, and all red or yellow cards, and all these kinds of stuff. Now for the annotation, we relied on 80 students that I reassure you were well paid, that were from the University of Liège, all engineering students. And basically we asked them to annotate all lines, circles, and goal parts, such as the crossbar or the goal posts, with polylines. So basically annotating points that are joined by a straight line, right? So for the lines, obviously, it's usually 2 points when the distortion of the camera is not too big. Otherwise, we approximate it with more points. And for the circles, you have all these points. And for the goal parts, usually 2 points is enough. So in total, we have 100,000 individual feed lines and 50,000 goal parts approximately. All these annotations went to at least a 2-step verification process. So this means that at least 2 different students have seen the final annotation after it was done to make sure that it was actually good annotation, right? And all these were annotated using the Super Annotate platform, which is a commercial product that we rely on. All right, so I will leave the floor to Florian now to present the different challenges.
Thank you, Anthony. So I'm Florian Majara. I work for EVS Broadcast Equipment, and I also pursue a PhD student at the University of Liège. So we decided at EVS Broadcast Equipment to sponsorize this challenge. So for us, this is an opportunity to foster work on camera calibration. And what we do aim is high quality camera calibration, so very precise results. So we believe that this is the way to achieve very nice graphical effects in augmented reality in order to enhance storytelling and also for rules enforcement, as some of you may have seen with the offside line this morning. So camera calibration is also a way to retrieve information about the game, such as statistics, and can also be used for tactical analysis. So we decided to split the challenge in 2 because usually in order to calibrate a camera, you use calibration targets. And in sport content, there is a big target that is the sports pitch, which has a very well-known shape and dimensions. So it's convenient to use it as a calibration target. And a first step is then to localize the soccer pitch elements. And then the second step is the camera calibration itself. So this is why we have two tasks. So the first one, the pitch localization, we got quite a big success with 12 competing teams, more than 100 submissions on the test set, and about 50 submissions on the challenge set. And for the camera calibration, there was 6 competing teams with about 50 submissions on the test set and about 20 on the challenge set. So I'm not sure this slide was necessary. I don't know. Can I just remove the... So the little box will stay, it's okay. So our sponsor is EVS, of course. So moving on to the first task. So for this task, there are 26 soccer pitch element classes, which are 20 lines or circle arcs that belong to the pitch plane. And there are 6 classes that belong to the goalposts. So each element is defined by its 2 extremities. So one team should provide the 2 extremities of each class that is present in the image. And as the center circle does not have 2 extremities, we discard this class for this task. So for the evaluation, the annotations are on the pixel level, but we believe that sometimes there's not only one pixel that can be identified as the extremity of a line. So we allow for some uncertainty in the predictions. So we say that that a prediction is correct if it's at less than t pixels from the correct annotation. So this allows us to frame the problem as a detection problem, and so we can compute an accuracy at a certain precision level. So we choose to have a final ranking score that is a weighted average of several levels of accuracies. So at 5 pixels, at 10 pixels, and at 20 pixels. So I'll let Anthony present the leaderboard.
Yeah, so it's time for announcing the results, right? So as Florian said, we have 12 competing teams this year, which are shown here. And as you can see, all of them beat our baseline, which is already a great result in itself, right? Because it means that we had some improvements on the task. And now we'll move on to the third team, which is the 2AI IPCA with Jose Enrique Brito and Miguel Santos Marquez from 2AI School of Technology, IPCA. In the second place now, we have the IMGO team with Lingqi Chen, Yi Yu, Qingyuan Wang, and Jin Cheng from MGTV. So congratulations to them. And now for the first place, drum roll, we have the one-day team with Yu Hui, Jinwen Wang, Jing Liu, Chao Qingye, Yingui Li, Cheng Zhao, and Qiao Tang from the Department of Computer Vision Technology VIS and the Department of Augmented Reality Technology Arts from Baidu Incorporation. So congratulations. And now we'll see if it works properly, but we have a video of them presenting their method.
Hello, everyone. I am very glad to report our work for SoccerNet Challenge 2022, pitch localization.
Should work.
Hello, everyone. I am very glad to report our work for SoccerNet Challenge 2022, pitch localization. First, briefly introduce this pitch localization task. It is aiming to detect the extremities of every soccer pitch element captured in the image, including 28 semantic labels. And the evaluation is dependent on the distance for the various class lines' extremities. To solve this problem effectively, we propose a pitch localization detector framework named PLD. Here, we observe that each line is unique, that is, there is at most one instance of a category of objects for a given image from the soccer pitch. Therefore, we treat it as an instance segmentation task at first that can correctly handle occlusions, where an object is spilled into 2 separate regions, and a detection model for optimizing extremities locations followed by a series of optimization strategy steps. A segmentation model is able to predict the extremities of the soccer pitch elements present in the image, but its positioning accuracy is limited, especially for ACC AT5, which can be concluded from the difference between ACC AT20 and ACC AT5 reaching 40 points. Therefore, we designed the following optimization strategy in our PLD to achieve better performance. Step 1. Refinement with point results means following the basic extremities results from the segmentation output, we further refine the extremities location with the point detection results. In step 2, we based on the simple counting of the identification lines categories judging the scene belonging to the left or the right side of the pitch, can correct the extremities category. Then, we update both extremities with the midpoint of 2 points for those which can be able to intersect and be close enough in step 3. Next, we focus on the top-down ambiguities, which are represented as mistakes, by recognizing the top lines as the bottom lines. And finally, we merge several output results in step 5 to reduce false negatives. Here are the results of the experiments. We take part in the test set images, and in a different perspective to show from the baseline extremities results to the final extremities results. In the end, to analyze the influence of each step of our PLD framework, we compare the performance between the baseline, which is from the segmentation result, and the optimization steps. Results in Table 1 show that the refinement with point guarantees better ACC at 5 performance and brings a remarkable 34.81% gain. Thanks for your attention.
Thank you, Baidu, for this great video.
Hello, everyone. I am very...
Once is enough. So what are the main takeaways for this first task? So I don't know if you've noticed, but no. Yes, there is quite a huge gap between the first team and the other ones. And in fact...
Hello, everyone. I am...
In fact, they are the only ones who choose to add another modality. So other teams, they only use semantic segmentation in order to find the extremities of the lines. And here they used bounding box detection, and they gain a really great performance gain. So maybe we can think that the future research could try other modalities such as direct line or ellipse parameters regression, or maybe to use more generic detectors like generic line detectors like SOLD. And this also relates to the second point. So a lot of the teams had problems with the symmetry of the soccer pitch. So maybe a simpler problem with less classes would lead to better results. So moving on to the second task. So given one frame, the participating teams should retrieve the internal and external camera parameters, including the position, the orientation, the lens parameters, and optionally provide distortion parameters. And we use a 3D model of the soccer pitch provided by the rule of the game described by the FIFA in order to evaluate the camera calibration. So we use the same annotations in order to evaluate the camera parameters. So we don't have any ground truths for the camera parameters, and we use the raw projection error as an indirect quality estimator of the camera parameters. So using the predicted camera parameters, we project the points that are sampled along the 3D model of the pitch, which gives a set of 2D polylines that we are going to assess. So once again, we say that a soccer pitch element is correctly detected if for each of the points that belong to the annotation, the distance between the annotated points and the polyline that has been projected is smaller than t pixels. So this is again a framing of the raw projection error as an accuracy. And in this task, in fact, the camera parameters estimation might fail. So we add another metric, which is the completeness rate, so the proportion of images for which the team was able to provide parameters. So the final ranking is a combination, a trade-off between both metrics. I don't know if you want to do the video go.
Sure. All right. So in this task, we had 6 participants, which makes sense that we have less because the second task is very reliant on the first task, right? So these teams were able to go all the way through. So you can recognize the IMGO and 2AI IPCA from the top 3 of the previous task, which means that we will have maybe new participants in the top 3, right? So the first one is Mike Azatov, who I think is watching us remotely right now from AI research at Arsenal FC. So let's congratulate him. Yeah, as you can see, there's a big gap between the third and the fourth position, which is really great. So now for the second position, we have the L3S team with Jonas Steiner, who also worked alone and achieved some very great results as well. Like, let's congratulate them. And now for the first task, there's a video. Oh yeah, right. We have the video of the second, so Jonas Steiner right now. That's for his method.
Hey, this is Jonas. I'm glad to present our main idea and results for the calibration challenge this year. I'm a PhD student at the IFRS Research Center in Hanover, Germany, supervised by Ralf Ebert. Recent approaches for spot field registration only perform homography estimation, which usually involves some kind of segmentation, initial estimation, and refinement. So it is worth following up existing approaches, or can we rethink this task? The initial idea is to start simple, which means to directly try to approximate the camera pose and focal length given the provided annotations from the challenge and not the raw image. As we have no key point correspondences, we aim to learn the parameters such that the reprojection error, our target task, is minimized. So we can define a differentiable objective function that computes the mean distance between given point annotations and its corresponding line segment. We can also compute the distance for circle segments, which are modeled as point clouds. Equally weighted each segment loss, we can compute gradients and update the camera parameters via gradient. Samples where the loss is higher than the user-defined thresholds are automatically rejected, which we call self-verification. Further, we use free initializations of the camera locations and keep the best result. Of course, there's some tricks to make things working better, but this is the main idea. This graphic shows the completeness rate and accuracy for multiple thresholds as there's a trade-off. As part of a challenge, we choose the value where the final score is maximized. The vertical line is an estimate of the maximum expected completeness rate, indicating the number of images showing one of the three camera types used. In summary, we are getting strong results, especially when using the ground truth annotations as input. But also the retrained segmentation baseline with more sampled points gives strong results. I personally think that it's important to be open about the limitations. And of course, we rely on accurate pitch element localization, but most important, we found some images where the optimization gets stuck in local minima, which are indeed rejected, but results in a lower completeness rate. So moving back to the related work, we think that an initial estimation could help to further push the results. Cheers.
All right. And so now for the final announcement of the winner of one of the SoccerNet Challenge 2022, we have Xiangwei Wang, Qin Liu, Hue, Chao Qingwei, Yingying Li, Chen Zhao, and Xiao Tan, also from the Department of Augmented Reality Technology and the Department of Computer Vision Technology of Baidu Inc. So let's congratulate them. So as you see, Baidu was able to win both tasks this year with their great model. And now we will hear a short presentation of their methods.
Hi, this is the Changmo team from Baidu. In this presentation, I will be presenting our method on the SoccerNet Challenge 2022 for camera calibration. We will first briefly introduce our proposed method in this presentation. Then, we show some results on an application. Our method has 3 steps: landmark processing, homograph calculation, and pose optimization. In the landmark processing step, we first calculate the intersections, vanishing points, and curve points based on the pitch elements detected on a frame. We call them landmarks. Then, we conduct a verification to reject the outlier. We illustrate the procedure of obtaining intersections in this page. The upper left image shows the detected elements on a frame. We compute line or conic models using these elements, and then produce intersections from the model. To obtain vanishing points, we use parallel lines as depicted in this page. The points on a curve are found using the curve segmentation. Due to the symmetric nature of soccer pitch, we have to deal with the field ambiguities. We resolve the top-down ambiguities by checking the rotation directions. We also check the correctness of the conic line intersections by comparing the distance of the two intersections and that of the maximum mutual distance of the curve points. We design three kinds solvers based on different landmark distributions and noises. The ransack solver is for removing the effects of outliers, and the shift solver is for a bad distribution of intersections. It is always difficult to choose one solver based on the observation in advance, so we deploy all solvers parallel at first and choose the one with the smallest reprojection error. To make use of vanishing points, we design a two-stage version solver, besides the traditional one, for both ransack solver and all points solver. For the shift solver, we add some small shift to the constrained landmarks and use all landmark including curved points for solver evaluation. We optimize the camera parameters with two sequential optimizations, including homograph optimization and pose optimization. This page shows our final result on the challenge set and the progressive improvements on the test set. Based on the calibration results, we repaint the soccer pitch and make this demo.
Great demo.
Yeah, very good.
So a few insights on the camera calibration challenge. So we noticed that all participants choose to follow the steps that we propose in our baseline. So first, a detection of the soccer pitch elements, and then the computation of camera parameters, but independently. So the detector quality has a big impact on the quality of the camera parameters estimations. So maybe a way to improve the results would be to combine the learning of both elements and to link them in order to provide the best results. And another remark is that no participant provided distortion coefficients in their final submission. And we believe that for future research, including distortion parameters could improve the final results. So I leave the floor to Anthony for the end of the challenge. But first, I would like to thank the SoccerNet team for this amazing challenge.
Thank you. All right, thank you, Florian. So yeah, I will conclude now the SoccerNet challenges. And before concluding, I really wanted to say that SoccerNet has been a very long journey since 2018, and it's not a journey that's going to end. So make sure to follow us if you want to be part of the next challenges and try to win, as just like Baidu did this year for the camera calibration task. So to follow us, you have several options. You have also, of course, GitHub, where all our code for downloading the data, evaluating the tasks, trying some baseline is available, and everything is very easy, can be very easily accessed through the pip package that we provide. We are also very not active on Twitter, but when we have important news, we post it there. Also, we have our YouTube channel where we are a bit more active and where we post some videos about our work that are related to video understanding in general with artificial intelligence. And also our Discord community I was talking about. So feel free to join. Everyone is welcome. So with that, I also want to thank all my co-organizers on this. So especially Silvio and Mark here from the university, but also EVS for sponsoring this great challenge and for sponsoring the workshop as well. So thank you very much. And I hope you have a nice CVPR starting tomorrow. Thank you.
So as I said, we still have the best paper award, and let me just let me just share everything that needs to be shared. So the best paper award has been sponsored by EVS Broadcast Equipment, and it's of $1,000. The decision has been made by combining the review scores, and then each of the keynote speakers, organizers, and papers have been able to vote on the different papers, and then these scores have been accumulated, and based on that, a winner has been found. But first, we also have a runner-up. So this time the runner-up is split between two different papers. It's split between the semi-supervised training to improve player and ball detection in soccer by Renaud Vandegren, Anthony Chopper, and Mark van Dodenbrock. And then also the monotrack shuttle trajectory reconstruction from monocular badminton video from Paul Liu and Yuxian Wang. So congratulations to both. And now for the winner. So this year it has been the SoccerNet tracking multiple object tracking dataset and benchmark in soccer videos by Anthony Chopper, Silvio Giancola, Adrian Gillies, Le Kang, Sheng Xu, Xiyu Cheng, Bernard Garnem, and Mark van Trockenberg. Olivia Banik to reward a diploma to the winners. You look like criminals. Cool. So that's it for today. Thank you a lot to everybody for a great workshop. Thank you to all of you for attending, both here in New Orleans and online. Thank you for the program committee for selecting, for performing our reviews. Thank you to the office for submitting, and to our keynote speakers for providing 4 great talks. And also thank you to EVS Equipment, Broadcast Equipment for sponsoring Best Paper Award. And then in the end, also thank you to the organizing committee who couldn't be here today, sadly, but who have put in a lot of work in order to organize this 8th edition of the Computer Vision for Sports workshop. So yes, that's it for today. Yeah, and I hope you have a great CVPR.
Thank you very much.